Somewhere far beyond the reach of human sight, galaxies are drifting apart so slowly that even across a lifetime, the change would be impossible to notice. Stars are quietly exhausting their fuel, not in explosions or flashes of light, but in silence, fading over millions and billions of years. And light, that began its journey long before Earth existed, is still traveling through space, crossing vast distances where there is no observer, no destination, and no urgency at all. These things are happening right now, whether we are aware of them or not. The universe does not rush, it does not repeat itself, and it does not wait to be understood. Most of what exists has never been seen, and most of what happens leaves no trace that anyone will ever notice. Entire regions of space remain completely dark, not because there is nothing there, but because the light has not yet arrived. There are forces shaping galaxies that we can't see directly, movements that only reveal themselves through subtle effects, and questions that remain unanswered not because they are complicated, but because the universe is vast beyond intuition. Tonight, we're not going to chase the loud mysteries or the dramatic ones. We're not here for explosions, collisions, or moments of sudden change. Instead, we'll move slowly through the quieter questions. The kind of mysteries that remain once everything else has settled. Questions about why space has the structure it does, why time seems to flow in one direction, and why, even with everything we've learned, so much still remains gently out of reach. These are not questions that need answers right now. They don't ask anything of you. They don't demand attention, effort, or understanding. They can simply exist in the background, like distant stars, barely visible, yet always present. You don't need to stay awake for any of this. You don't need to remember details, follow explanations, or hold on to any particular thought. This isn't a lesson, and there's no story you need to track from beginning to end. The universe doesn't mind if you stop paying attention. Everything we'll talk about tonight will continue whether you're listening or not. Stars will keep burning. Galaxies will keep turning. Space will keep expanding at its own quiet pace. You're welcome to listen for as long as it feels comfortable, or to let the words soften and blur as your body begins to rest. There's no correct way to experience this. You don't need to visualize anything clearly. You don't need to imagine distances or scales accurately. If your thoughts wander, that's fine. If you miss something, nothing is lost. The information here isn't going anywhere, and neither is the night. You might notice your attention drifting in and out, catching fragments of ideas, letting others pass by without effort. That's exactly how this is meant to work. The universe unfolds slowly, without urgency, and this space is designed to do the same. There's nowhere else you need to be right now, no decision you need to make, no outcome you need to reach, just a gradual slowing and a sense of distance from the day that's already passed. We'll begin by exploring some of the deeper mysteries of the universe as a whole. Questions about the nature of space itself, about time, matter, and the forces that quietly shape everything we can see. We'll move gently through ideas that stretch far beyond everyday experience, without rushing toward conclusions or clear resolutions. And later, without any sudden change or clear dividing line, we'll drift closer to home, toward the Milky Way, a single galaxy among hundreds of billions. A vast, rotating system of stars, gas, and dark regions that we're still learning how to understand. It contains ancient stars that formed near the beginning of cosmic history, and regions where new stars are slowly coming into existence even now. You don't need to notice when one part of the journey becomes another. There's no marker you need to listen for, no moment you need to stay awake to catch. The transition will happen quietly, the way most things in the universe do, at its own pace. If you find yourself drifting off along the way, that's perfectly fine. The universe doesn't require witnesses. It doesn't need to be observed to continue. Just let the ideas come and go, without effort, without judgment. And as we begin, you can allow the night to do what it naturally does. Slow things down, dim the edges of thought, and make space for rest. The universe is mostly empty. This is one of the first quiet mysteries. When we look out into space, what we see is not crowded or chaotic. It is vast and calm and almost entirely made of nothing. Between the stars, there is space. Between the galaxies, even more space. And in that space, there is mostly just darkness and distance, and the faint hum of radiation left over from the beginning of everything. If you could stand in the middle of intergalactic space, far from any galaxy, far from any star, you would see almost nothing. A few faint smudges of light in every direction, but mostly just black. Deep, quiet, endless black. And yet, even in that emptiness, there is something. There is a faint glow, a whisper of light. It comes from every direction at once, and it has been traveling through space for more than 13 billion years. We call it the cosmic microwave background. It is the afterglow of the Big Bang, the leftover heat from the moment the universe began, and it fills all of space, evenly, quietly, like a memory that never fades. When the universe was very young, it was hot. So hot that atoms could not form. So hot that light could not travel freely. Everything was a dense fog of energy and particles, glowing white hot, packed together in a space smaller than we can imagine. But then the universe expanded. It cooled. And after about 380,000 years, it cooled enough for atoms to form, for light to finally break free. That light has been traveling ever since. It has stretched and cooled as the universe expanded. What was once visible light, bright and blazing, is now microwave radiation, invisible to our eyes, but detectable by our instruments. And it is everywhere. No matter where you point a telescope, no matter where you look in the sky, you will find it. The same faint glow, the same ancient light. It is the oldest thing we can see, the earliest snapshot of the universe. And it tells us that the cosmos was once much smaller, much hotter, and much more uniform than it is today. But it also raises a mystery. The cosmic microwave background is almost perfectly smooth, almost perfectly uniform. The temperature is the same in every direction, to within a fraction of a degree. And that shouldn't be possible, because the universe is very large, so large that light from one side of the observable universe has not had time to reach the other side. So, how did both sides end up at the same temperature? How did distant regions of space, regions that could never have communicated with each other, end up so perfectly balanced? This is called the horizon problem. And the answer, scientists believe, lies in something that happened in the first fraction of a second after the Big Bang. Something called inflation. Inflation is the idea that the universe, in its earliest moments, expanded faster than the speed of light, much faster. In less than a trillionth of a second, the universe grew from something smaller than an atom to something larger than a galaxy. This rapid expansion smoothed out any irregularities. It stretched space itself so quickly that everything became uniform. And then, just as suddenly, inflation stopped. The universe continued to expand, but at a slower, steadier pace. And the evidence for this is written in the cosmic microwave background, because even though the background is smooth, it is not perfectly smooth. There are tiny fluctuations, tiny variations in temperature, regions that are slightly warmer or slightly cooler than average. These fluctuations are the seeds of everything that came later, the seeds of galaxies, the seeds of stars, the seeds of planets and moons, and eventually, life. Gravity pulled matter toward the denser regions. Over millions of years, those regions grew. They collapsed. They formed the first stars, the first galaxies, the cosmic web of structure we see today. But the pattern of those fluctuations, the way they are distributed across the sky, matches exactly what inflation predicts. It is one of the most elegant confirmations in all of cosmology. A theory about the first instant of time, confirmed by light that has traveled for more than 13 billion years. And yet, we still do not know what caused inflation. We do not know what force or field or phenomenon could make space expand so fast. We do not know why it started. We do not know why it stopped. Inflation solves the horizon problem, but it also opens new mysteries. And that is how science works. Each answer leads to deeper questions. Each solution reveals new puzzles. The universe does not give up its secrets easily, but it does give them up slowly, quietly, one discovery at a time. Another mystery, quieter still, concerns the nature of time itself. We experience time as a flow, a river moving in one direction, past to present to future, always forward, never back. But the laws of physics do not require this. Most of the equations that describe the universe work just as well if time runs backward. If you filmed a planet orbiting a star and played the footage in reverse, the motion would still obey the laws of gravity. If you filmed particles colliding and reversed the tape, the physics would still hold. And yet, we never see time run backward. We never see a broken glass reassemble itself. We never see heat flow from a cold object to a hot one. We never see the past change. This is called the arrow of time, and it is one of the deepest mysteries in physics. The arrow of time is not a law. It is a tendency, a statistical inevitability. It arises not from the fundamental rules of the universe, but from the way those rules play out over large numbers of particles. It is connected to a concept called entropy. Entropy is a measure of disorder, of randomness, of the number of ways a system can be arranged. A broken glass has high entropy. There are many ways the pieces can be scattered. A whole glass has low entropy. There is only one way for it to be intact. The second law of thermodynamics says that entropy always increases. Systems move from order to disorder, from low entropy to high entropy, never the reverse. And this is why time has an arrow. When you break a glass, you are increasing entropy. The pieces scatter, the energy spreads out, and the universe moves toward a more disordered state. To reassemble the glass, you would need to decrease entropy. You would need to gather all the pieces, all the energy, all the vibrations, and put them back exactly as they were. This is not impossible. It does not violate any fundamental law, but it is extraordinarily unlikely. So unlikely that it will never happen by chance. And so, time flows forward, because entropy increases, because disorder grows, because the universe is moving from a state of low entropy to a state of high entropy. But this raises another mystery. If entropy always increases, then the universe must have started in a state of very low entropy, a state of very high order, and we do not know why. Why was the early universe so orderly? Why was everything so smooth, so uniform, so finely arranged? This is called the past hypothesis, the assumption that the universe began in a low entropy state. And it is one of the most important assumptions in all of physics. Without it, the second law of thermodynamics would not work. Without it, time would have no arrow. Without it, the universe would make no sense. And yet, we do not know why it is true. We do not know what set the initial conditions. We do not know why the Big Bang began with such low entropy. Some scientists believe the answer lies in quantum mechanics. Others believe it lies in the nature of gravity. Still others believe it is simply a brute fact, a boundary condition that requires no explanation. But the mystery remains. Time flows forward. Entropy increases. The universe grows more disordered with every passing moment. And we do not know why it started any other way. There is a place in space where time behaves even more strangely. Near a black hole, time slows down. Not for the person falling in. For them, time feels normal. But for someone watching from far away, time near the black hole appears to stretch, to crawl, to nearly stop. This is called time dilation, and it is a consequence of Einstein's theory of general relativity. General relativity tells us that gravity is not a force. It is a curvature of space-time. Massive objects bend the fabric of space and time around them, and the stronger the gravity, the more extreme the curvature. Near a black hole, gravity is so strong that space-time is bent almost to breaking, and time, as a result, slows down. If you could watch someone fall toward a black hole, you would see them slow down as they approached the event horizon. Their movements would become sluggish. Their clock would tick more and more slowly. And at the event horizon itself, they would appear to freeze. But, from their perspective, nothing unusual would happen. They would fall through the event horizon in a finite amount of time. They would continue falling toward the singularity at the center, and they would never see themselves freeze. This is one of the strangest features of black holes. The event horizon is not a physical barrier. It is simply the point of no return, the boundary beyond which nothing, not even light, can escape. And yet, from the outside, it looks like time itself has stopped there. This leads to a paradox. If you watch someone fall into a black hole, you will never see them cross the event horizon. You will see them slow down, redden, and fade, but never quite as disappear. And yet, from their perspective, they do cross. They do fall in. They do reach the singularity. So what is the truth? Do they cross or not? The answer, according to general relativity, is both. It depends on your perspective. It depends on where you are and how you measure time. This is the nature of space-time. It is not absolute. It is not the same for everyone. It is relative, flexible, dependent on motion and gravity and the path you take through the universe. And near a black hole, this relativity becomes extreme. Time is not a river, it is a dimension, a part of the fabric of reality. And like space, it can be stretched, compressed, and curved. Black holes are the places where this curvature is most severe, where time and space become so warped that our intuitions break down, where the rules of everyday experience no longer apply. And yet, black holes are not rare. There are millions of them in our galaxy alone, perhaps billions. They are a natural consequence of stellar evolution, the final stage in the life of the most massive stars. When a star runs out of fuel, it can no longer support itself against gravity. It collapses. And if it is massive enough, it collapses all the way down to a point, a singularity, a place where density becomes infinite, and the laws of physics, as we know them, cease to function. Around that singularity, space-time is so curved that nothing can escape, and the event horizon forms. From the outside, a black hole is invisible. It emits no light. It reflects no light. It is a hole in space, a region of absolute darkness. But we can detect black holes by their effects, by the way they bend light, by the way they pull on nearby stars, by the way they heat up gas as it spirals inward, glowing brightly just before it disappears forever. And we have even taken a picture of one. In 2019, the Event Horizon Telescope captured an image of the black hole at the center of the galaxy M87. It showed a dark circle surrounded by a glowing ring of light, the shadow of the event horizon, the boundary of no return. It was the first direct image of a black hole, and it confirmed what general relativity had predicted more than a century earlier. Black holes are real. They exist, and they are exactly as strange as the equations said they would be. But they are also quiet, patient, waiting in the darkness, slowly consuming anything that comes too close. They do not explode. They do not shout. They simply exist, warping space-time, bending light, slowing time. And they will be here long after the stars have burned out, long after the galaxies have faded, long after the universe has grown cold and dark, because black holes evaporate very, very slowly. This evaporation is another mystery, another quiet puzzle. Stephen Hawking discovered that black holes are not entirely black. They emit radiation, a faint glow of particles that leak out from the event horizon. This radiation is called Hawking radiation, and it arises from the quantum nature of empty space. Empty space is not truly empty. It is filled with virtual particles, pairs of particles and antiparticles that pop into existence and annihilate each other almost instantly. Normally, These virtual particles have no lasting effect. They appear and disappear too quickly to notice. But near the event horizon of a black hole, something different happens. One particle of the pair can fall into the black hole, while the other escapes. The escaping particle becomes real. It carries energy away from the black hole. And because energy is conserved, the black hole loses mass. Over time, very slowly, the black hole evaporates. For a large black hole, this process takes an unimaginably long time, longer than the current age of the universe, longer than the lifetime of the stars. But for a small black hole, the process is faster. And in the far, far future, when all the stars have died and the universe is cold and dark, black holes will be the last sources of energy, the last points of light. And then, one by one, they too will fade. This evaporation leads to a paradox, a mystery that has puzzled physicists for decades. When a black hole evaporates, what happens to the information that fell into it? In quantum mechanics, information cannot be destroyed. It can be scrambled, hidden, or transformed, but it must always be preserved. But if a black hole evaporates completely, where does the information go? Does it escape in the Hawking radiation? Does it remain inside, somehow encoded in the final burst of energy? Or is it lost forever? This is called the black hole information paradox. And it is one of the deepest unsolved problems in theoretical physics. Some scientists believe the information is preserved, that it is encoded in the radiation in a way we do not yet understand. Others believe the paradox reveals a flaw in our understanding of quantum mechanics or general relativity. Still others believe the answer lies in a theory we have not yet discovered, a theory that unites quantum mechanics and gravity, a theory of everything. But for now, the paradox remains. Black holes keep their secrets. They swallow information. They warp time. They bend light. And they do it all in silence. Silence is another feature of space. Sound cannot travel in a vacuum. There is no air to carry the vibrations, no medium for the waves to move through. And so, space is quiet. Perfectly, utterly quiet. The explosions of supernovae, the collisions of galaxies, the roar of gas falling into black holes, all of it happens in silence. We see the light. We detect the radiation, but we hear nothing. This silence is part of what makes space so peaceful, so calming. There is no noise, no distraction, just light and darkness and the slow dance of gravity. But there is one exception: gravitational waves. Gravitational waves are ripples in space-time itself. They are created when massive objects accelerate, when black holes collide, when neutron stars spiral together, when the fabric of space is shaken by violent events. These ripples travel at the speed of light, spreading outward in all directions, and as they pass through space, they stretch and compress everything in their path, including us. When a gravitational wave passes through Earth, it changes the distance between objects, very slightly, by less than the width of an atom, but enough to detect. And we have detected them. In 2015, the LIGO Observatory recorded the first direct detection of gravitational waves. They came from two black holes, more than 1 billion light-years away, that had spiraled together and merged. The signal lasted less than a second, a faint chirp, a rising tone, and then silence. But in that chirp was a wealth of information. The masses of the black holes, the distance to the collision, the shape of space-time as it rippled and settled. It was the first time we had heard the universe, not with light, not with particles, but with gravity itself. Since then, dozens more gravitational waves have been detected, from black holes, from neutron stars, from events we are still working to understand. And each one is a voice, a signal, a message from the distant universe, carried not by light, but by the fabric of space and time. Gravitational waves are silent in the traditional sense. They do not vibrate air. They do not make sound. But they do vibrate space-time. And when we convert their signal into audio, they make a sound, a chirp, a whistle, a hum. It is the sound of the universe itself, singing. And it is one of the most profound discoveries in modern science, because it opens a new way of observing the cosmos, a way that does not rely on light, a way that can see through dust and gas and darkness, a way that lets us listen to the universe, not just look at it. And what we are hearing is beautiful, quiet, steady, the slow collision of massive objects, the merger of black holes, the spin of neutron stars, all of it happening in the deep, dark silence of space, all of it sending ripples through the fabric of reality, ripples that travel for billions of years, that cross unimaginable distances, that arrive here, faint and fading, just strong enough for us to detect. And in those ripples, we find answers and more mysteries, because the universe is full of both. One of the quietest mysteries involves something we cannot see at all: dark matter. Most of the matter in the universe is invisible. It does not emit light. It does not absorb light. It does not reflect light. It passes through ordinary matter as if it were not there. And yet, we know it exists. We know because of the way galaxies move, the way they spin, the way they hold together. When astronomers measure the speed of stars orbiting the center of a galaxy, they find something strange. The stars at the edge of the galaxy are moving too fast, much too fast. According to the laws of gravity, those stars should be moving slower, or they should fly off into space. The visible matter in the galaxy, the stars and gas and dust, does not produce enough gravity to hold them in place. And yet, they stay. They orbit. They remain bound to the galaxy. The only explanation is that there is more matter there, matter we cannot see, matter that provides the extra gravity needed to keep the galaxy together. This invisible matter is called dark matter, and it makes up about 85% of all the matter in the universe. We do not know what it is made of. We do not know what particles compose it. We have never detected it directly, but we see its effects everywhere. In the rotation of galaxies, in the motion of galaxy clusters, in the bending of light around massive objects, in the structure of the cosmic web. Dark matter is woven through the universe. It forms a scaffolding, a framework, upon which galaxies form. It pulls ordinary matter together. It shapes the large-scale structure of the cosmos. Without dark matter, galaxies would not exist. Stars would not exist. We would not exist. And yet, we do not know what it is. Scientists have proposed many candidates. exotic particles with names like WIMPs and actions, primordial black holes, modified theories of gravity. But so far, none of these ideas have been confirmed. Experiments deep underground search for dark matter particles. Detectors in space look for signs of dark matter annihilation. Particle accelerators try to create dark matter in the lab, but the universe keeps it secret. Dark matter remains invisible, silent, undetected. It does not interact with light. It does not interact with ordinary matter, except through gravity. It is a ghost, a shadow, a presence we can infer but never touch. And it is everywhere. Right now, dark matter is passing through you. Billions of particles streaming through your body, through the earth, through everything, without leaving a trace. You cannot feel it, you cannot see it, but it is there, and it has been there since the beginning. Dark matter was present in the early universe. It clumped together under gravity. It formed the first structures. It pulled hydrogen gas into the first galaxies. It is older than the stars, older than the planets, older than anything we can see. And it will be here long after everything else has faded, because dark matter does not decay. It does not burn out. It does not evaporate. It simply exists, patient, invisible, eternal. There is another invisible component to the universe, something even stranger than dark matter: dark energy. Dark energy is the name we give to the force that is causing the universe to expand faster and faster. For most of the history of the universe, the expansion was slowing down. Gravity was pulling everything together, trying to halt the expansion, perhaps even reverse it. But about 5 billion years ago, something changed. The expansion began to accelerate. Galaxies began to move away from each other more quickly. The space between them began to grow at an increasing rate. And this acceleration has continued ever since. Scientists discovered this in the late 1990s by studying distant supernovae. These exploding stars are so bright that they can be seen across billions of light years, and they have a predictable brightness, which makes them useful as distance markers. When astronomers measured the distance to these supernovae and compared it to their redshift, the amount their light had been stretched by the expansion of the universe, they found something unexpected. The distant supernovae were farther away than they should have been. The universe had expanded more than expected. The only explanation was that the expansion was accelerating, that some unknown force was pushing space apart. This force is called dark energy, and it makes up about 68% of the total energy in the universe. We do not know what it is. We do not know where it comes from. We do not know why it exists. It could be a property of space itself, a kind of energy that is built into the fabric of the vacuum. Einstein called it the cosmological constant. Or it could be a new kind of field, a dynamic energy that changes over time. Scientists call this quintessence. Or it could be a sign that our understanding of gravity is incomplete, that general relativity needs to be modified on the largest scales. But we do not know. What we do know is that dark energy is causing the universe to expand faster and faster, and this has profound consequences for the future. As the universe expands, galaxies move farther apart. The space between them grows, and eventually, Distant galaxies will be moving away from us faster than the speed of light. Not because they are moving through space, but because space itself is expanding. And when that happens, their light will never reach us. They will disappear beyond the cosmic horizon. They will be lost to us forever. In the far future, billions of years from now, the only galaxies we will be able to see are the ones in our local group: the Milky Way, Andromeda, and a few dozen smaller galaxies, all bound together by gravity. Everything else will have vanished. The universe will appear empty, dark, quiet, and eventually, even those nearby galaxies will merge. They will collide and combine into a single, giant, elliptical galaxy. And then, there will be nothing else to see. No other galaxies, no other stars beyond our own. The universe will still be expanding. Dark energy will still be pushing space apart. But we will be alone. This is called the Big Chill, or the heat death of the universe. It is the ultimate fate of a universe dominated by dark energy. A future where everything grows cold and dark and still. The stars will burn out. One by one, they will exhaust their fuel and fade. The smallest stars, the red dwarfs, will last the longest, trillions of years. But eventually, even they will die. And when the last star goes out, the universe will be dark. There will be no more light, no more heat, no more energy flowing from one place to another. Only black holes will remain, and even they will evaporate slowly over timescales so long that the current age of the universe is less than a blink. And then there will be nothing, just empty space, cold, dark, expanding forever. This is the fate predicted by our current understanding of dark energy. A quiet end, a slow fade, a universe that does not end in fire but in silence. But we do not know if this is truly what will happen, because we do not understand dark energy. We do not know if it is constant. We do not know if it will change. Perhaps dark energy will grow stronger. Perhaps it will tear apart galaxies, stars, planets, atoms. Perhaps it will end the universe in a big rip. Or perhaps dark energy will weaken. Perhaps the expansion will slow again. Perhaps gravity will eventually win, and the universe will collapse back in on itself, ending in a big crunch. Or perhaps something else will happen. Something we have not imagined. Something that depends on physics we have not yet discovered. The future is uncertain. The universe keeps its secrets. But for now, the expansion continues. Dark energy pushes. Space grows. And we drift slowly toward a future we cannot see. There is a question that arises naturally from all of this. Why does the universe have the properties it does? Why is the cosmological constant the value it is? Why is dark energy so weak? If dark energy were slightly stronger, the universe would have expanded too quickly for galaxies to form. If it were slightly weaker, the universe might have collapsed long ago. If the laws of physics were slightly different, stars might not ignite, atoms might not form, life might never arise. The universe seems finely tuned, balanced on a knife edge, perfectly calibrated to allow complexity, structure, and life. This is called the fine-tuning problem, and it is one of the most profound mysteries in cosmology. Some scientists believe the answer is the anthropic principle. The idea that the universe must have the properties it does, because if it did not, we would not be here to observe it. In other words, we exist because the universe allows us to exist. And if the universe were different, we would not be asking the question. This is not a satisfying answer to everyone. It feels circular. It does not explain why the universe is the way it is, only why we are able to observe it. Others believe the answer lies in the multiverse, the idea that our universe is just one of many, that there are countless other universes, each with different laws of physics, different constants, different properties. In most of those universes, conditions are not right for life. Stars do not form. Galaxies do not form. Complexity does not arise. But in a few universes, by chance, the conditions are just right. And in those universes, life can emerge. Observers can exist. We live in one of those rare universes, not because it was designed for us, but because we could only exist in a universe like this. The multiverse is a controversial idea. It is difficult to test, difficult to prove or disprove. Some scientists embrace it. Others reject it as unscientific. But it is one possible answer to the fine-tuning problem. One way to explain why the universe has the properties it does. Another possibility is that we simply do not understand the laws of physics well enough, that there is a deeper theory, a more fundamental explanation, that will show why the constants have the values they do. Perhaps string theory will provide that answer. Perhaps loop quantum gravity. Perhaps something else entirely. But for now, the mystery remains. The universe is finely tuned, and we do not know why. There is a related mystery about the number of dimensions. We experience 3 dimensions of space: length, width, height, and 1 dimension of time. But some theories of physics suggest there may be more dimensions. Dimensions we cannot perceive. Dimensions that are curled up, hidden, too small to detect. String theory, for example, requires 10 dimensions, or 11 in some versions. In string theory, the fundamental building blocks of the universe are not particles, but tiny, vibrating strings. These strings exist in a space with more than 3 dimensions, and the way they vibrate determines what kind of particle they appear to be. An electron is a string vibrating one way. A quark is a string vibrating another way. A photon is a string vibrating yet another way. The extra dimensions are compactified, curled up into shapes so small that we cannot see them, smaller than atoms, smaller than protons, smaller than anything we can measure. But they are there, and they affect the way the strings vibrate. They affect the properties of particles. They affect the laws of physics. If string theory is correct, then the universe is much stranger than it appears. Space is not 3-dimensional. It is 10-dimensional, or 11, and most of those dimensions are hidden from us. But string theory is not proven. It is a mathematical framework, a set of equations. It makes predictions, but many of those predictions are difficult or impossible to test with current technology. And so the question remains, are there extra dimensions? And if so, why are they hidden? One possibility is that the extra dimensions are small because of the way the universe evolved. Perhaps they started out the same size as the other dimensions, but something caused them to curl up, to compactify. Another possibility is that the extra dimensions are not small at all, that they are large, but we are confined to a three-dimensional surface within them, like a sheet of paper in a three-dimensional room. We can move along the paper, but not off it. This is called the brain world scenario. The idea that our universe is a three-dimensional brain embedded in a higher dimensional space. If this is true, then gravity might be able to leak into the extra dimensions. And this could explain why gravity is so much weaker than the other forces. Electromagnetism, the strong force, and the weak force are all confined to our brain. But gravity spreads out into the higher dimensions, and so it appears weaker to us. This is a speculative idea. There is no direct evidence for it, but it is consistent with the mathematics of string theory, and it offers a possible explanation for one of the puzzles of particle physics. The question of extra dimensions is still open. We do not know if they exist. We do not know how many there are. We do not know why they would be hidden. But the possibility is tantalizing. The idea that the universe has more structure, more complexity, more depth than we can perceive. That reality extends beyond what we can see, beyond what we can measure, beyond what we can imagine, and that somewhere in those hidden dimensions there are truths we have not yet discovered. Another quiet mystery involves the nature of quantum mechanics itself. Quantum mechanics is the theory that describes the behavior of particles at the smallest scales, and it is one of the most successful theories in all of science. It has been tested countless times. It has made predictions that have been confirmed to extraordinary precision. It underlies all of modern technology: computers, lasers, smartphones, medical imaging. All of it depends on quantum mechanics. And yet, we do not fully understand what it means. At the heart of quantum mechanics is the idea of superposition, the idea that a particle can exist in multiple states at once. It can be in two places at the same time. It can spin in two directions at the same time. It can be both a wave and a particle. But when we measure the particle, when we observe it, the superposition collapses. The particle chooses one state, one position, one spin, and we do not know why. This is called the measurement problem, and it is one of the deepest puzzles in quantum mechanics. What counts as a measurement? What causes the collapse? Is it the act of observation, the interaction with a detector, the involvement of consciousness? No one knows. There are many interpretations of quantum mechanics, many ways of thinking about what is happening. The Copenhagen interpretation says that the wave function, the mathematical description of the superposition, is not real. It is just a tool for calculating probabilities. The collapse happens when we measure, but there is no deeper reality behind it. The many worlds interpretation says that the wave function never collapses. Instead, every possible outcome happens. The universe splits into multiple branches. In one branch, the particle is here. In another branch, it is there, and both branches are equally real. The pilot wave interpretation says that particles do have definite positions, even when we are not measuring them. They are guided by a wave, a field that fills all of space. The wave is real. The particle is real, and there is no collapse. Each interpretation gives the same predictions. Each one matches the experiments. but they paint very different pictures of reality, and we do not know which one is correct, or if any of them are correct. Quantum mechanics works. It predicts, it explains, but it does not tell us what is really happening. It does not tell us what reality is like when no one is looking. And this is deeply unsettling, because it suggests that the universe is fundamentally strange, that reality is not what it seems, that the act of observation plays a role in shaping what exists, or perhaps it suggests that our language, our concepts, our intuitions are simply inadequate, that the quantum world does not fit into the categories we use to describe the everyday world. Particles are not tiny billiard balls. Waves are not ripples in water. Superposition is not a particle being in two places at once. These are just metaphors, approximations, ways of translating the mathematics into words. But the mathematics is what is real. The equations are what describe the universe, and they do not care about our intuitions. Quantum mechanics is a mystery we live with, a theory we use every day without fully understanding what it means. And perhaps that is enough. Perhaps the universe does not owe us an explanation. Perhaps reality is simply what the equations say it is: strange, counterintuitive, impossible to visualize, but real nonetheless. One of the strangest predictions of quantum mechanics involves something called entanglement. Entanglement is a connection between particles, a correlation that persists even when the particles are separated by vast distances. If two particles are entangled, measuring one of them instantly affects the other, no matter how far apart they are. This does not mean information is traveling faster than light. It does not mean there is a signal passing between them. The connection is more subtle than that. But it is real. It has been tested. It has been confirmed. Einstein called it spooky action at a distance. He did not like it. He thought it suggested that quantum mechanics was incomplete, that there must be some hidden variables, some deeper reality that explained the correlation. But experiments have shown that Einstein was wrong. There are no hidden variables. The entanglement is fundamental. It is built into the fabric of quantum mechanics, and it is one of the most profound features of the universe. Entanglement means that particles are not independent. They are connected. They are part of a larger whole. Even when separated by light years, they remain linked. They share a quantum state. They are, in some sense, one system. This has deep implications for the nature of reality. It suggests that the universe is not made of separate, isolated objects. It is a web of connections, a network of relationships. Particles do not have properties on their own. They have properties in relation to other particles, in relation to the whole. This is a shift in perspective, a move away from the idea of a universe made of independent parts toward the idea of a universe that is fundamentally interconnected. And it is not just a philosophical idea. It is a physical fact, confirmed by experiment, used in technology. Quantum computers rely on entanglement. Quantum cryptography relies on entanglement. Future technologies will rely on it even more. But we still do not fully understand it. We do not know why entanglement exists. We do not know what it means for the nature of space and time. Some physicists believe that entanglement is more fundamental than space, that space itself emerges from the pattern of entanglement between particles. This is a radical idea. It suggests that space is not a container, not a stage on which events unfold. It is a consequence, a byproduct, an emergent property of quantum connections. If this is true, then the universe is even stranger than we thought. Space is not fundamental. Distance is not fundamental. Only the web of entanglement is real, and everything else is built on top of that. This is still speculative, still theoretical, but it is a direction that research is moving, a possibility that physicists are exploring, and it is one more mystery, one more quiet puzzle, one more hint that the universe is deeper, richer, more interconnected than we ever imagined. There is a type of particle that passes through everything. Right now, trillions of them are passing through your body, through the walls, through the earth, through everything solid, as if it were not there at all. They are called neutrinos. Neutrinos are among the most abundant particles in the universe. They are produced in the cores of stars, in supernovae, in the Big Bang itself. They stream out from the sun in vast numbers, flooding through space, through planets, through us, and they barely interact with anything. A neutrino could pass through a light year of solid lead and not hit a single atom. They are ghostly, insubstantial, almost impossible to detect. And yet, we have detected them, deep underground, in massive tanks of water. Scientists have built detectors. They wait, they watch. And occasionally, very rarely, a neutrino will collide with a water molecule. It will produce a flash of light, a brief spark, and the detector will record it. These detections are precious. Each one tells us something about where the neutrino came from, what produced it, how long it has been traveling. Neutrinos from the sun tell us about the nuclear reactions happening in its core. Neutrinos from supernovae tell us about the deaths of massive stars. Neutrinos from the early universe carry information about the Big Bang itself. They are messengers, travelers from distant places and distant times. And because they interact so weakly, they can carry information that light cannot. Light can be absorbed, scattered, blocked by dust and gas. But neutrinos pass through everything. They arrive here unchanged, carrying their message intact. And that message is often surprising. In the 1960s, scientists built the first detector to measure neutrinos from the sun. They wanted to test their understanding of how stars work, to confirm that the sun was powered by nuclear fusion. But when they measured the number of neutrinos arriving from the sun, they found a problem. There were too few. Only about 1/3 of the expected number were arriving. The rest were missing. This became known as the solar neutrino problem, and it puzzled scientists for decades. Some thought the problem was with the detector. Perhaps it was not sensitive enough. Perhaps it was missing some neutrinos. Others thought the problem was with the theory. Perhaps the sun was not fusing hydrogen the way we thought. Perhaps our models were wrong. But the answer turned out to be stranger than either of those possibilities. The neutrinos were not missing. They were changing. Neutrinos come in 3 types, 3 flavors: electron neutrinos, muon neutrinos, and tau neutrinos. The sun produces electron neutrinos. But as those neutrinos travel from the sun to the Earth, they oscillate. They change from one flavor to another, and by the time they arrive here, only about 1/3 of them are still electron neutrinos. The detector was only sensitive to electron neutrinos, so it was only seeing 1/3 of the total. The rest had changed flavor and were passing through undetected. This discovery solved the solar neutrino problem, but it also revealed something profound about neutrinos themselves. For neutrinos to oscillate, they must have mass. This was unexpected. For many years, scientists thought neutrinos were massless. The equations of particle physics suggested they should be massless, like photons. But the oscillations proved otherwise. Neutrinos have mass, a very small mass, so small that it is difficult to measure. But it is there, and this has implications for the universe as a whole. If neutrinos have mass, then they contribute to the total mass of the universe. And because they are so abundant, even a tiny mass adds up. Scientists estimate there are about 330 neutrinos per cubic centimeter in the universe, left over from the Big Bang, cooled by the expansion of space, no longer hot and energetic, but still present, still moving, still everywhere. If each of those neutrinos has even a tiny mass, then together they account for a significant fraction of the matter in the universe. Not as much as dark matter, but more than all the visible stars and gas combined. Neutrinos are part of the cosmic inventory, part of the structure, part of the web of matter that shapes the universe. And yet, they are almost invisible, almost intangible, passing through everything, affecting almost nothing, but always there. They are quiet travelers, silent messengers, witnesses to events we can barely imagine. And they remind us that the universe is full of things we cannot see, cannot touch, cannot directly perceive. But they are real, they exist, and they matter. Another mystery involves something much larger than a particle. It involves the largest structures in the universe. Galaxies are not scattered randomly through space. They are arranged in patterns, in clusters, in filaments, in vast webs of structure that stretch across hundreds of millions of light years. These structures are called the cosmic web, and it is one of the most striking features of the universe. If you could step back far enough, if you could see the universe on the largest scales, you would see that galaxies are not evenly distributed. They form sheets and filaments, like the strands of a spider's web. And between those strands are enormous voids, regions of space that are nearly empty. The cosmic web formed over billions of years, shaped by gravity and dark matter. In the early universe, matter was distributed almost uniformly, almost smooth, but there were tiny fluctuations, tiny variations in density. Gravity pulled matter toward the denser regions. Over time, those regions grew. They attracted more matter. They became denser still, and the less dense regions became emptier. Matter flowed out of them toward the denser areas. Slowly, over hundreds of millions of years, the structure emerged. Filaments formed, clusters formed, voids formed, and the pattern that emerged was the cosmic web. It is a natural consequence of gravity, a structure that arises inevitably from the initial conditions of the universe. But it is also beautiful, delicate, complex. The filaments are like threads of light stretching across the darkness. The clusters are like knots where many threads come together. And the voids are like empty chambers, vast and silent. The cosmic web is held together by dark matter. The filaments are made mostly of dark matter. with galaxies and gas embedded within them. The dark matter provides the gravity, the scaffolding, the framework, and it is stable. The cosmic web does not collapse. It does not fall apart. It simply exists, slowly evolving as the universe expands. Galaxies move along the filaments. They flow toward the clusters. They merge. They interact. They are drawn together by gravity, guided by the structure of the web. And we are part of this structure. The Milky Way is part of a small cluster called the local group. The local group is part of a larger structure called the Virgo supercluster. And the Virgo supercluster is part of an even larger structure called Laniakea. Laniakea is a supercluster of superclusters, a vast region of space, 500 million light-years across, containing about 100,000 galaxies, and we are moving through it. The Milky Way is being pulled toward the center of Laniakea, toward a region called the Great Attractor. We are flowing along one of the filaments of the cosmic web, drawn by gravity, moving through space at hundreds of kilometers per second. This motion has been ongoing for billions of years, and it will continue for billions more. We are not stationary. We are not isolated. We are part of a flow, a current, a river of galaxies moving through the structure of the universe. And this flow is one of the quiet motions of the cosmos. Slow, steady, inevitable. It is not something we can feel, not something we experience directly, but it is happening all the time, beneath everything else. The cosmic web is a reminder that the universe has structure on the largest scales, that even the voids, the empty spaces, are part of a pattern, that everything is connected. And it is also a reminder that we are small, that our galaxy is one of many, that the structures we are part of extend far beyond what we can see. But there is something comforting in that, something peaceful. We are part of something larger. We are woven into the fabric of the universe, and that fabric has been unfolding for billions of years and will continue to unfold for billions more. We do not need to understand all of it. We do not need to grasp the full scale. We simply need to know that we are part of it, and that is enough. One of the mysteries of the cosmic web involves the voids themselves. The voids are not completely empty. They contain some galaxies, some matter, but they are far less dense than the filaments and clusters, and they are very large. Some voids are hundreds of millions of light-years across, enormous bubbles of near emptiness, surrounded by walls of galaxies. Inside a void, space is quieter, calmer. There is less gravity pulling things together, less structure forming. Galaxies and voids are often isolated. They evolve more slowly. They have fewer interactions, fewer mergers, fewer disturbances. In some ways, a void is the most peaceful place in the universe, away from the crowded clusters, away from the constant gravitational tug and pull, just empty space, stretching in every direction. But the voids are also mysterious. We do not know exactly how they formed. We know that gravity shaped them, but the details are still being worked out. We do not know if they will always exist, or if they will eventually be filled in as the universe continues to evolve. We do not know if there is something special about the voids, if they play a role in the structure of the universe that we do not yet understand, but they are there, vast and empty and quiet, a natural part of the cosmic web, and they remind us that the universe is not uniform, that it has texture, that it has regions of density and regions of emptiness, and both are necessary. Both are part of the pattern. Another quiet mystery involves the motion of galaxies within clusters. When astronomers measure the speeds of galaxies in a cluster, they find something strange. The galaxies are moving too fast. According to the laws of gravity, based on the visible matter in the cluster, the galaxies should be moving slower, or they should escape. The cluster should fly apart. But it does not. The galaxies remain bound. They stay together. This was one of the first clues that dark matter exists, that there is more matter in the cluster than we can see. Invisible matter, providing the extra gravity needed to hold the cluster together. This observation was made in the 1930s by an astronomer named Fritz Zwicky. He studied the Coma cluster, a large cluster of galaxies, and measured the speeds of the galaxies within it. He found that they were moving much faster than expected, and he concluded that there must be missing mass, dark matter. At the time, his idea was not widely accepted. It seemed strange, unlikely. Why would there be invisible matter? But over the decades, more evidence accumulated. The rotation curves of galaxies, the bending of light around massive objects, the structure of the cosmic web, all of it pointed to the same conclusion. Dark matter exists, and it is everywhere. Galaxy clusters are some of the best places to study dark matter because they contain so much of it, and because the effects are so clear. When light from a distant galaxy passes near a massive cluster, the light is bent by gravity. This is called gravitational lensing. The cluster acts like a lens, focusing and distorting the light. And by studying the amount of distortion, astronomers can map the distribution of mass in the cluster. What they find is that most of the mass is not in the galaxies. It is in the space between them, in the dark matter. The dark matter forms a halo around the cluster, a smooth, invisible cloud that extends far beyond the visible galaxies, and this halo provides the gravity, the structure, the glue that holds the cluster together. Without dark matter, clusters would not exist. Galaxies would not stay together. The cosmic web would not have formed. Dark matter is essential, fundamental, invisible but present, and it is one of the quiet forces shaping the universe. There is a question about the future of galaxies. What will happen to them in the far future as the universe continues to expand? The answer depends on dark energy, on whether the acceleration of the universe continues, on whether space keeps expanding faster and faster. If dark energy remains constant, then the future is clear. The universe will keep expanding. Galaxies will move farther apart, and eventually, they will be so far away that their light can no longer reach us. The only galaxies we will see are the ones in our local group, the Milky Way, Andromeda, and a few dozen smaller galaxies. And even those galaxies will merge. In about 4 billion years, the Milky Way and Andromeda will collide. They will pass through each other, their stars mingling, their gas clouds colliding and forming new stars. And then they will fall back together. They will merge into a single, large elliptical galaxy. This new galaxy will be the center of our local universe, the only structure we can see, the only light in the darkness. All other galaxies will have vanished beyond the cosmic horizon. The universe will appear empty, silent, still. And then, over trillions of years, the stars in that galaxy will burn out. One by one, they will exhaust their fuel and fade. The smallest stars, the red dwarfs, will last the longest, tens of trillions of years, but eventually even they will die. And when the last star goes out, the universe will be dark. No more light, no more heat, just cold, dead remnants, white dwarfs, neutron stars, black holes, and empty space expanding forever. This is the quiet end, the slow fade, the universe growing cold and dark and still. It is not an end in fire, not an end in violence, just an end in silence. And it will take a very, very long time. But it is also possible that something else will happen. That dark energy will change. That new physics will intervene. Perhaps the universe will collapse. Perhaps it will rip apart. Perhaps it will cycle, ending and beginning again. We do not know. The future is uncertain. The universe keeps its secrets. But for now, the stars are still burning. The galaxies are still turning. And we are here in this brief moment to witness it. That is a gift, a quiet gift, a moment of light in the vast darkness of time. And we can rest in that. We can let go. We can simply be here, now, without needing to know what comes next. The universe will continue. It will unfold. It will do what it does. And we can rest. There is a type of star that barely shines. It is called a brown dwarf. And it is not quite a star, not quite a planet. It is something in between. Brown dwarfs form the same way stars do, from collapsing clouds of gas and dust, but they do not have enough mass to ignite hydrogen fusion in their cores. They are too small, too light. The pressure and temperature at their center never reach the point where hydrogen atoms can fuse into helium. And so, they do not shine the way stars do. They do not burn steadily for billions of years. Instead, they glow faintly with leftover heat from their formation. They slowly cool. They fade. Brown dwarfs are dim, very dim, difficult to detect. They emit most of their light in the infrared, invisible to our eyes. But they are out there, scattered throughout the galaxy, silent, cooling, almost invisible. Some brown dwarfs are alone, drifting through space, never part of a solar system, never orbiting a star. Others are companions, orbiting larger stars, or orbiting each other in binary pairs. They are the failed stars, the objects that almost made it, but did not quite have enough mass. And yet, they are fascinating, because they blur the line between stars and planets. They show us that the universe does not have sharp categories, that there is a continuum, a spectrum of objects, each slightly different from the next. Brown dwarfs are also important for understanding how stars form, how planets form, how solar systems come together. They are part of the population, part of the inventory of objects in the galaxy, and they remind us that not everything in the universe is bright, not everything shines. Some things are dim, quiet, almost invisible, but they are still there, still real. still part of the story. Another dim object in the universe is a white dwarf. A white dwarf is the remnant of a star like the Sun. After the star has exhausted its fuel, after it has shed its outer layers, what remains is the core. The core is incredibly dense. A white dwarf with the mass of the Sun is only about the size of the Earth. All that mass compressed into such a small volume. The density is staggering. A teaspoon of white dwarf material would weigh several tons. White dwarfs do not burn. They do not produce energy through fusion. They simply glow with leftover heat. Heat that was trapped in the core during the star's lifetime. And they cool, very slowly. A white dwarf starts out hot, tens of thousands of degrees. It shines with a bright white light. But over time, it cools. It fades. It shifts from white to yellow to red. And eventually, after trillions of years, it will cool completely. It will become a black dwarf, a cold, dark, dead star. No black dwarfs exist yet. The universe is not old enough. Even the oldest white dwarfs are still faintly glowing, but in the far future, they will exist. The final remnants of stars, cold and dark and silent. White dwarfs are stable. They are held up by something called electron degeneracy pressure, the pressure that comes from the quantum behavior of electrons. Electrons cannot occupy the same space. They resist being compressed, and this resistance is what keeps a white dwarf from collapsing further. But there is a limit. If a white dwarf gains too much mass, if it exceeds about 1.4 times the mass of the Sun, the electron degeneracy pressure is not enough. The star collapses, and it explodes. This explosion is called a Type 1, a supernova, and it is one of the brightest events in the universe. Type Ia supernovae are important for cosmology because they are so bright and so consistent. They can be seen across vast distances, and they can be used as distance markers, as standard candles, to measure the expansion of the universe. It was by studying type Ia supernovae that scientists discovered dark energy, that the expansion of the universe is accelerating. But before the explosion, before the supernova, there is just a white dwarf, cooling quietly, fading slowly, waiting. And most white dwarfs will never explode. Most will simply cool and fade and become black dwarfs billions of years from now. They are the quiet endings, the peaceful deaths of ordinary stars. And they remind us that not all endings are violent, that most things fade gently, that silence is more common than noise. There is another type of stellar remnant, more extreme than a white dwarf, more dense, more strange. A neutron star. Neutron stars form when very massive stars explode as supernovae. The core collapses, and if it is heavy enough, it does not stop at the white dwarf stage. It collapses further. The protons and electrons in the core are squeezed together so tightly that they combine. They become neutrons, and the entire core becomes a ball of neutrons. A neutron star is incredibly dense, far denser than a white dwarf. A neutron star with the mass of the Sun is only about 20 kilometers across, about the size of a city, and a teaspoon of neutron star material would weigh as much as a mountain. The surface of a neutron star is smooth, hard, made of atomic nuclei packed so tightly that they form a solid crust. Beneath the crust, the matter is even more exotic. A superfluid of neutrons, a sea of particles that flows without friction, without resistance. And at the very center, the core, the conditions are so extreme that we do not know what happens. The matter may break down into quarks. It may form something entirely new, something we have no name for. Neutron stars are also incredibly strong. The magnetic field of a neutron star is trillions of times stronger than Earth's magnetic field. Some neutron stars spin very fast, hundreds of times per second. They are called pulsars. Pulsars emit beams of radiation from their magnetic poles, and as the star spins, those beams sweep across space like a lighthouse beam. If the beam sweeps past Earth, we detect a pulse, a brief flash of radio waves or X-rays, and we see the star blinking on and off very rapidly, very precisely. Pulsars are some of the most accurate clocks in the universe. Their pulses are so regular, so consistent, that they can be used to test the laws of physics, to detect gravitational waves, to measure the expansion of space. But not all neutron stars are pulsars. Some spin more slowly. Some have weaker magnetic fields. Some do not emit beams that point toward Earth. Those neutron stars are silent, invisible. We only know they are there if they are part of a binary system, if they are pulling gas from a companion star. Neutron stars are the densest objects in the universe. Aside from black holes, they are the edge of matter, the limit of how compressed ordinary matter can be. Beyond that limit, there is only one possibility: a black hole. And black holes are where the quiet mysteries become even deeper. There is a mystery about what happens inside a black hole. We know what happens at the event horizon. We know how time behaves, how light behaves, how gravity pulls. But inside, beyond that boundary, we can only speculate. General relativity tells us that at the center of a black hole is a singularity, a point of infinite density, a place where space and time break down, where the equations stop working. But we do not know if singularities truly exist. Perhaps something else happens. Perhaps quantum mechanics prevents the collapse from reaching infinite density. Perhaps the matter bounces back. Perhaps it tunnels to another universe. These are speculations, possibilities. But we have no way to test them, because nothing can escape from inside a black hole. No information, no signal, no light. Whatever happens inside remains hidden, forever sealed behind the event horizon. This is called cosmic censorship. The idea that singularities are always hidden, that the universe does not allow us to see them directly. It is as if the universe has a modesty, a reluctance to reveal its most extreme states, its most violent breakdowns. And perhaps that is for the best. Perhaps there are some things we are not meant to see, some places where the laws we know simply do not apply. Black holes are boundaries, edges, places where our understanding ends and mystery begins, and they are comfortable with that. They do not demand to be understood. They simply exist, quiet, patient, keeping their secrets. Another mystery involves the rotation of black holes. Black holes can spin, and when they spin, they drag space-time around with them. This is called frame dragging. The spinning black hole twists the fabric of space and time, pulling everything nearby into a rotating motion. Near a spinning black hole, it becomes impossible to stand still. Space itself is rotating, and anything in that space is carried along with it. This creates a region called the ergosphere, a zone outside the event horizon where nothing can remain stationary, where everything must move in the direction of the black hole's rotation. But the ergosphere is not inside the event horizon. It is possible to enter the ergosphere and escape. It is possible to extract energy from it. This is called the Penrose process, and it is one of the most remarkable features of spinning black holes. By dropping an object into the ergosphere and carefully timing its trajectory, it is possible to extract rotational energy from the black hole. The object can split into two pieces. One falls in. The other escapes, carrying away more energy than it started with. The black hole loses a tiny amount of its spin, and the escaping object gains energy. This is a theoretical process. It has never been observed, but it is allowed by the laws of physics. It is possible. And in the far future, if intelligent beings still exist, if they need energy and the universe is cold and dark, they might use this process. They might harvest energy from spinning black holes, because black holes will be the last sources of energy, the last warm places in a frozen universe. But that is a very long time from now, trillions upon trillions of years. For now, black holes are simply there, spinning quietly, warping space-time, waiting. There is also a mystery about where black holes come from in the first place. We know that stellar mass black holes form from supernovae, from the collapse of massive stars. But what about the supermassive black holes at the centers of galaxies? These black holes are enormous, millions or billions of times the mass of the Sun, and they formed very early in the history of the universe. We see supermassive black holes in galaxies that are less than 1 billion years old, galaxies that formed shortly after the Big Bang, and we do not know how they grew so large so quickly. It takes time for a black hole to grow. It must consume matter, pull in gas and stars, merge with other black holes. But there does not seem to have been enough time for these supermassive black holes to reach their size through normal processes. So how did they form? One possibility is that they started large, that they formed from the direct collapse of massive clouds of gas in the early universe. Another possibility is that they formed from the collapse of the first stars, stars that were much more massive than any star today, stars that lived fast and died young, leaving behind large black holes. Or perhaps they grew through repeated mergers. Perhaps many smaller black holes came together again and again, building up mass quickly. We do not know. The observations are still unclear. The theories are still being tested. But it is one more mystery, one more question about the history of the universe. And it reminds us that even the largest, most powerful objects in the cosmos have origins we do not fully understand. Supermassive black holes are also surprisingly influential. At the center of almost every large galaxy, there is a supermassive black hole, including our own. The Milky Way has a black hole called Sagittarius A star. It has a mass of about 4 million suns, and it sits at the very center of the galaxy, quiet, mostly dormant, occasionally consuming a small amount of gas or a stray star. But in other galaxies, the central black hole is more active. It pulls in large amounts of matter. Gas spirals inward, heating up, glowing brightly. Jets of particles shoot outward at nearly the speed of light. These active black holes are called quasars, or active galactic nuclei. They are among the brightest objects in the universe. A single quasar can outshine an entire galaxy of stars, and yet the light does not come from the black hole itself. It comes from the matter falling into the black hole. The accretion disk, the swirling, glowing ring of gas just outside the event horizon. As the gas spirals inward, it heats up. Friction converts gravitational potential energy into heat. The temperature rises. The gas glows. And just before it crosses the event horizon, just before it disappears forever, the gas emits a final burst of light, a last farewell. That light travels outward, across space, across billions of light years, and it reaches us. Quasars are so bright that we can see them at the edge of the observable universe. They are beacons, markers of the early cosmos, signs of black holes that were already supermassive when the universe was young. But they are also temporary. Quasars do not last forever. As the black hole consumes the nearby gas, the supply runs out. The accretion disk fades. The jets shut off. The quasar becomes quiet. And the galaxy settles into a quieter state. The black hole remains, but it is no longer feeding, no longer glowing. It becomes dormant, like Sagittarius, a star, like the black holes at the centers of most galaxies today. They are sleeping giants, waiting, ready to wake if new gas arrives. But for now, still, there is a connection between black holes and the galaxies around them. When astronomers measure the mass of a supermassive black hole and compare it to the properties of its host galaxy, they find a correlation. The more massive the black hole, the more massive the central bulge of the galaxy. The two are linked. This is surprising, because the black hole is tiny compared to the galaxy. The event horizon of a supermassive black hole is only a few light hours across. The galaxy is hundreds of thousands of light years across. And yet, they seem to know about each other. They seem to have co-evolved. This suggests that black holes play a role in shaping galaxies, that their activity, their jets, their radiation, affects the gas and stars around them. When a quasar is active, its jets can blow gas out of the galaxy. They can heat the gas, preventing it from collapsing and forming new stars. This is called feedback. The black hole regulates the growth of the galaxy. It prevents the galaxy from forming too many stars too quickly. And this feedback may explain the correlation. The black hole and the galaxy grow together. They influence each other. They reach a balance. When the black hole is too small, it does not provide enough feedback. The galaxy forms stars quickly. The black hole grows. When the black hole is too large, it provides too much feedback. Star formation slows. The galaxy stops growing. And eventually, they settle into a stable state, a balance, a quiet equilibrium. This is one of the surprising discoveries of modern astronomy, that black holes, the darkest objects in the universe, play a bright role in the evolution of galaxies, that destruction and creation are linked, that endings and beginnings are part of the same process. There is a type of galaxy that is shaped by black holes, an elliptical galaxy. Elliptical galaxies are smooth, round. They do not have spiral arms. They do not have much gas or dust. They are made mostly of old stars, and they are common. About a third of all large galaxies are elliptical. Elliptical galaxies form through mergers. When two spiral galaxies collide, they mix. Their stars pass through each other. Their gas clouds collide and form new stars. And over time, the two galaxies merge. They become one, and the result is an elliptical galaxy. During the merger, gas falls toward the center. It feeds the supermassive black holes. The black holes grow. They become active. They emit jets and radiation, and that activity blows out the remaining gas, the gas that would have formed new stars. So the elliptical galaxy ends up with very little gas, very few young stars, just old stars orbiting in random directions. The galaxy is quiet, settled, red, and at its center, a supermassive black hole, dormant, having consumed its meal, having shut off the star formation, having shaped the galaxy into its final form. Elliptical galaxies are the end state, the retirement, the quiet phase. They are what galaxies become after a lifetime of activity, after mergers and star formation and black hole growth. They are peaceful, stable, slowly fading, and they will remain that way for a very long time. There is a question about whether we live in a typical place in the universe. Our solar system is in the outskirts of the Milky Way, about halfway out from the center, in a quiet region, away from the dense clusters of stars near the core. This is a good place to be, quiet, stable, safe. Near the center of the galaxy, stars are packed closely together. Gravitational interactions are common. Stellar encounters could disrupt planetary systems. Supernovae are more frequent. It is a more dangerous place, more chaotic. Out here, in the suburbs of the galaxy, things are calmer. The stars are farther apart. Disturbances are rare, and that may be important for life, for planets like Earth, for stable conditions over billions of years. If we were closer to the center, Earth might not have had the long, stable history that allowed life to evolve. So in some sense, we live in a special place, a Goldilocks zone, not too close to the center, not too far out in the empty regions, just right. But this raises a question. Is this typical? Do most life-bearing planets form in places like this? Or are we unusually lucky? We do not know. We do not yet know how common life is in the universe. We do not know how sensitive it is to location. But it is something to think about, something to wonder. That perhaps our place in the universe is not random. That perhaps the conditions here are part of why we exist. That location matters. That structure matters. That the universe has regions more favorable to life, and we happen to be in one of them. And that is another quiet mystery, another piece of the puzzle. There is also a mystery about the shape of the Milky Way itself. The Milky Way is a spiral galaxy. It has a central bulge, a disk, spiral arms, a halo of old stars. But the disk is not flat. It is warped, twisted. At the edges, far from the center, the disk curves upward on one side and downward on the other. This warp is subtle, but it is there, and we do not fully know why. One possibility is that the warp is caused by the gravity of nearby galaxies. The Magellanic Clouds, two small galaxies that orbit the Milky Way may be pulling on the disk, distorting it. Another possibility is that the warp is a leftover from a past collision, a merger with a smaller galaxy long ago that left the disk slightly bent. Or perhaps the warp is simply a natural feature, something that happens to spiral galaxies over time as they rotate and evolve. We do not know. The observations are difficult. The disk is large, and we are inside it, which makes it hard to see its overall shape. But the warp is there, a gentle curve, a twist, and it reminds us that even familiar objects we see every night, can hold surprises. The Milky Way is our home galaxy, but we are still learning about it, still discovering its structure, still mapping its shape, and there are still mysteries, still questions. Another mystery involves the halo of the Milky Way. The halo is a spherical region surrounding the disk. It is made of old stars, globular clusters, and dark matter. The stars in the halo are ancient, some of the oldest stars in the universe. They formed more than 13 billion years ago, shortly after the Big Bang, and they are moving in random directions, not rotating with the disk, not following the spiral structure, just orbiting the center of the galaxy in elliptical paths. These stars are remnants, survivors. They are what remains of the early universe, the first generation of stars, and they tell us about the history of the Milky Way, about how it formed, about what it was like when it was young. By studying the halo stars, astronomers can reconstruct the past. They can see traces of ancient mergers, events that happened billions of years ago, smaller galaxies that were consumed by the Milky Way, leaving behind streams of stars in the halo. The halo is a fossil record, a history book, a record of everything the Milky Way has experienced, and it is still being written. Even now, the Milky Way is consuming smaller galaxies. The Magellanic Clouds will eventually be absorbed. Their stars will join the halo. This is a slow process, a quiet process, a gradual accumulation, and it is how large galaxies grow, by consuming smaller ones, by merging, by gathering mass over time. The universe is not static. It is not frozen. It is evolving, changing, slowly rearranging itself. And we are part of that process, part of the flow, part of the ongoing story. There is a question about whether the Milky Way will always look the way it does now. The answer is no. Galaxies change, they evolve, and the Milky Way is no exception. In about 4 billion years, the Milky Way will collide with Andromeda. This collision is inevitable. The two galaxies are moving toward each other, pulled together by gravity. And when they meet, they will not simply bounce off. They will pass through each other. Their stars will intermingle. Their gas clouds will collide. And over the course of several passes, several 100 million years, they will merge. They will become one galaxy. This new galaxy has already been given a name, Milkomeda, or sometimes Milk-Dromeda. It will be an elliptical galaxy, larger than either the Milky Way or Andromeda, red, smooth, filled with old stars, and the Sun, if it still exists, will be part of it, orbiting in some new path, in some new region. But this is nothing to fear. The collision will not harm the solar system. Stars are so far apart that the chance of any collision is almost zero. The Sun will simply find itself in a new galaxy, with a new sky, new constellations, new neighbors, and life on Earth, if it still exists, will look up and see a different universe, a different arrangement of stars. But that is billions of years away. For now, the Milky Way is stable. Andromeda is still far away, and the collision is a distant future. There is time, so much time, and in that time the universe will continue, slowly, quietly, unfolding. There is a mystery about the very edge of the universe, the observable universe. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It is about 93 billion light-years across, and it is expanding. Every moment, more of the universe comes into view. More light arrives from distant regions. But there is a limit, a horizon. Beyond that horizon, light has not yet had time to reach us, and we will never see it, because the universe is expanding, and the more distant regions are moving away from us faster than light can travel through space. So there is a boundary, a cosmic horizon, and beyond it, the universe continues. But we cannot see it, cannot know what is there. This is humbling. It means that the universe we observe is only a small part of the total universe. The full universe may be vastly larger, perhaps infinite, and we will never know. We can only see our small patch, our observable bubble. But that bubble is still enormous. It contains hundreds of billions of galaxies, trillions of stars, more planets than we can count. And within that bubble, there is so much to explore, so much to discover, so many mysteries. We do not need to see the whole universe to be amazed by it, to be humbled by it, to find peace in it. The part we can see is enough, more than enough, and it is ours to wonder about, to study, to rest in. There is a type of light we cannot see with our eyes, infrared light. It is all around us, emitted by warm objects, by stars, by planets, by our own bodies. Everything that has heat emits infrared radiation. It is invisible to us, but it is there. A constant glow, a thermal signature. In space, infrared light is important because it can pass through dust. Visible light is blocked by dust clouds, scattered, absorbed. When we look at certain regions of space with optical telescopes, we see darkness, opacity, walls of dust. But when we look with infrared telescopes, we can see through. We can peer into the hearts of dust clouds, into star-forming regions, into the centers of galaxies. Infrared light reveals what is hidden. It shows us the stars being born, the planets forming, the warm gas swirling in the depths of molecular clouds, and it shows us the cool objects, the objects too dim to see in visible light. Brown dwarfs, cold planets, distant galaxies shrouded in dust. The universe looks different in infrared, warmer, fuller, more textured, and it reminds us that what we see is only part of what is there, that light comes in many forms, that our eyes show us just one slice of reality. There are other forms of light, other wavelengths, radio waves, microwaves, ultraviolet, X-rays, gamma rays. Each one reveals something different. Each one shows us a different aspect of the universe. Radio telescopes see cold gas, the clouds between the stars, the hydrogen that fills the galaxy, the faint signals from pulsars and distant galaxies. X-ray telescopes see hot gas, the million-degree plasmas in galaxy clusters, the material falling into black holes, the remnants of supernovae. Gamma-ray telescopes see the most energetic events, the explosions, the collisions, the places where particles are accelerated to nearly the speed of light. Together, these different forms of light give us a complete picture, a full view of the universe. Not just what shines, but what glows faintly, what radiates, what exists in the darkness. And that picture is richer than we ever imagined, more complex, more layered. The universe is not just made of things we can see, it is made of things we can detect, things we can infer, things we can measure. And each measurement reveals more. Each observation adds to the story. There is a mystery about the very first light. The cosmic microwave background is the oldest light we can see, but it is not the first light that was ever emitted. Before the cosmic microwave background, the universe was opaque. Light could not travel freely. It was scattered immediately, trapped in the dense fog of particles. But there was light. Light from the Big Bang itself. Light from the earliest moments. That light still exists, but it has been redshifted, stretched by the expansion of the universe, shifted to longer and longer wavelengths. By now, that earliest light has been stretched into wavelengths we cannot detect, longer than radio waves, longer than anything our instruments can measure. It is still there, filling the universe, a ghost of the beginning, but invisible, beyond our reach. And perhaps it always will be. Perhaps there are limits to how far back we can see, how far back we can probe. The cosmic microwave background is a wall, a boundary in time, the earliest moment we can observe directly. Before that, the universe is hidden, veiled, opaque, and we can only infer what happened, only model, only calculate. We cannot see it, cannot photograph it, cannot witness it. It is a mystery that may remain forever, a question we may never fully answer. But that is part of the beauty of science, part of the humility it teaches us. There are limits to what we can know, boundaries to our understanding, and that is okay. We do not need to know everything. We do not need to see everything. We can rest in the knowledge we have and be at peace with the mysteries that remain. There is another mystery about the nature of space itself. Is space continuous, or is it discrete? At the largest scales, space appears smooth, continuous. You can move through it in any direction. You can divide it into smaller and smaller regions, infinitely. But some theories suggest that space is not truly continuous, that at the smallest scales, space is made of discrete units, tiny chunks, pixels of reality. This is an idea from quantum gravity, the attempt to unite quantum mechanics and general relativity. In quantum mechanics, energy comes in discrete units, quanta. Photons are quanta of light. Electrons are quanta of electric charge. Perhaps space itself is also quantized. Perhaps there is a smallest possible length, a fundamental unit below which space cannot be divided further. This length is called the Planck length. It is incredibly small, about 10 to the minus 35 meters, far smaller than an atom, far smaller than anything we can measure. If space is quantized, if it is made of Planck-sized units, then the universe is fundamentally grainy, pixelated, like a digital photograph when you zoom in too far. But we do not know if this is true. We have no way to test it. The scales are too small. The energies required to probe those scales are far beyond anything we can produce. It is a theoretical idea, a possibility, a hint of what might lie at the very foundation of reality. And it is another reminder that the universe may be stranger than we can imagine, that the fabric of space and time may have a structure we cannot see, a hidden architecture. Or perhaps space is truly continuous. Perhaps there is no smallest length. Perhaps you can divide forever. We do not know. The mystery remains. But it is a quiet mystery, a gentle puzzle, not something we need to solve tonight, just something to wonder about, something to drift through as we rest. There is a phenomenon that connects the very small and the very large. Quantum fluctuations. At the quantum level, empty space is not truly empty. It is filled with fluctuations, tiny bursts of energy, virtual particles that appear and disappear in an instant. These fluctuations are random, unpredictable. They arise from the uncertainty principle, the idea that at the quantum level, nothing is perfectly still. Nothing is perfectly certain. And these tiny fluctuations, these random variations, are what seeded the structure of the universe. During inflation, when the universe was expanding faster than light, quantum fluctuations were stretched, amplified, frozen into the fabric of space. Those frozen fluctuations became the tiny variations in density that we see in the cosmic microwave background. And those variations, over time, grew. They attracted matter. They formed the seeds of galaxies, the seeds of stars, the seeds of everything we see. So the structure of the universe, the pattern of galaxies and voids, the cosmic web itself, all of it arose from quantum fluctuations, from randomness at the smallest scale. This is one of the most profound connections in physics, the link between the quantum world and the cosmic scale. It shows us that the smallest things matter, that tiny fluctuations can have enormous consequences, that randomness and order are intertwined, and it is beautiful, elegant, a deep truth about how the universe works. From uncertainty comes structure. From chaos comes form. From the random dance of quantum fields comes the majestic architecture of galaxies. It is a reminder that the universe is whole, that everything is connected, that there are no separate realms, only different scales of the same reality. And we can rest in that. We can let go of the need to separate things, to categorize, to divide. The universe is one thing, and we are part of it. There is a question about whether the laws of physics are the same everywhere. We assume they are. We assume that the speed of light is the same in distant galaxies, that gravity works the same way, that atoms behave the same way, And all the evidence supports this. When we observe distant galaxies, we see the same physical processes, the same spectral lines, the same behavior. But we cannot be certain. We can only observe a small part of the universe, the observable universe, our cosmic bubble. Beyond that, we do not know. Perhaps the laws are different. Perhaps the constants have different values. Perhaps physics works in a completely different way. This is speculation, but it is allowed, because we cannot check. And if the multiverse exists, if there are many universes with different properties, then the laws almost certainly vary. Each universe would have its own physics, its own constants, its own rules. We would live in just one of them, the one where the laws allow us to exist. But we would never know about the others. We would never see them, never interact with them. They would be forever separate, forever beyond our reach. This is a strange idea, a disorienting idea, but also a humbling one. It suggests that our universe, the one we know, the one we study, is not special, not unique, just one among many. And the laws we discover, the constants we measure, are not fundamental truths about reality. They are just the local rules, the conditions of our particular universe. This changes the meaning of a law of nature. It makes it contingent, dependent, specific to our corner of existence. And it raises questions we may never answer. Questions about why our laws are what they are, why our universe is the way it is. But again, these are questions we can hold lightly. We do not need to solve them. We can simply let them be. The universe we live in is enough. The laws we have discovered are enough. The mysteries we can explore are enough. And we can rest in that. There is a type of star that pulses, a variable star. Variable stars change in brightness. They dim and brighten over and over in regular cycles. Some variable stars pulse because they are unstable. They expand and contract. Their outer layers move in and out like a slow heartbeat. As the star expands, it cools and dims. As it contracts, it heats and brightens. This cycle can take days, or weeks, or months, and it is remarkably regular, predictable, a cosmic clock. One type of variable star is especially important: Cepheid variables. Cepheids are large, bright stars, and their pulsation period is directly related to their intrinsic brightness. The longer the period, the brighter the star. This relationship makes Cepheids useful as distance markers. If you observe a Cepheid and measure its period, you know how bright it truly is. And if you know how bright it truly is, and you measure how bright it appears, you can calculate how far away it is. This is how Edwin Hubble measured the distances to other galaxies. He found Cepheids in Andromeda. He measured their periods. He calculated their distances. And he discovered that Andromeda was far away, so far that it could not be part of the Milky Way. It had to be a separate galaxy. This was a revolutionary discovery. It showed that the universe was much larger than anyone had thought, that the Milky Way was just one galaxy among many, and it opened the door to modern cosmology, to the study of the universe as a whole. Cepheids are still used today. They are one of the first steps on the cosmic distance ladder. the series of methods we use to measure distances to farther and farther objects. And they are reliable, steady, pulsing quietly in the darkness, telling us how far away they are. There are other variable stars that vary for different reasons, eclipsing binaries, two stars orbiting each other. When one passes in front of the other, the combined light dims. When they are side by side, the light is brighter. Flare stars, small stars that occasionally brighten suddenly, emitting bursts of energy. Novae, white dwarfs that accumulate matter from a companion star and occasionally explode, brightening dramatically before fading again. Each type of variable tells us something. Each one reveals a different aspect of stellar physics, and together they remind us that stars are not static. They are dynamic, changing, evolving. The night sky may appear still, unchanging, but if you watch carefully, if you measure precisely, you see that it is alive, that stars breathe, pulse, flare, that the universe is always in motion, always transforming. And we can watch, we can observe, we can rest in the knowledge that even the stars are restful in their changes, that their cycles are slow, predictable, gentle. There is a mystery about the fate of planets. There is a place where all the mysteries converge. In your mind, in your awareness, in this moment. All the questions we have explored, all the puzzles, all the unknowns, they exist because we are here to ask them, to wonder about them. The universe existed for billions of years, before conscious beings, before observers, before anyone to notice the stars, the galaxies, the slow unfolding of space and time. And it will exist for billions more, after we are gone, after consciousness has faded, after the last observer has disappeared. But right now, in this brief moment, the universe is aware of itself, through us, through you. You are made of atoms, forged in stars, scattered through space, gathered by gravity, assembled into planets, into oceans, into cells, into thoughts. You are stardust, contemplating stars, the universe, looking at itself, asking questions, seeking understanding. This is extraordinary, rare, perhaps unique in all the cosmos, or perhaps common. We do not know, but either way, it is precious, this moment, this awareness, this quiet wondering, and it does not require effort, does not require struggle, does not require staying awake. The universe will continue, with or without your attention, your consciousness, your awareness. It has no need of witnesses, of observers, of understanding. It simply is, and you can simply be part of it, resting in it, held by it. There is a rhythm to everything. The expansion of the universe, the rotation of galaxies, the orbits of stars, the cycles of planets, day and night, seasons, tides, life and death, waking and sleeping, all of it, part of the same rhythm, the same flow, the same dance, and you are dancing, even now, even as you rest. Your heart beats, your lungs breathe, your cells divide and repair, your brain processes, sorts, consolidates, all without your direction, all without your effort. The body knows what to do. The universe knows what to do, and you can trust that knowing, can surrender to that rhythm. There is nothing to control, nothing to force, nothing to make happen, just the natural unfolding of rest, of restoration, of sleep, like the slow cooling of a white dwarf, like the gentle drift of galaxies through space. Everything happens in its own time, at its own pace, and sleep will come when it comes, not before, not after, just when it is ready. There is a concept in astronomy called deep time, the vast spans of cosmic history, billions of years, timescales so long that human experience disappears into them like a grain of sand on an infinite beach. But deep time also reminds us that this moment, this brief flicker, this instant of consciousness is no less real, no less valid for being temporary. A mayfly lives for one day, but that day is its entire life, its whole existence, complete, whole, perfect, and we live for decades, perhaps a century, a brief moment in cosmic time, but our moment is complete, whole, perfect. This night, this rest, this sleep is part of that, part of your moment, part of your experience, and it deserves your gentleness, your acceptance, your peace. You do not need to achieve anything tonight, not even sleep, just rest, just stillness, just being here. And if sleep comes, it comes, and if it does not, that is also okay. The body will rest, regardless, will restore itself in its own way. There is a mystery about gratitude. Why do we feel grateful for existence, for beauty, for the universe? Gratitude serves no evolutionary purpose, provides no survival advantage, and yet we feel it, perhaps. Gratitude is the universe appreciating itself through us, a moment of recognition, of acknowledgement that all of this vast complexity, this elegant structure, this beautiful mystery exists, and we are here to witness it for however brief a time. That is worth gratitude, worth wonder, worth peace. The stars do not know they are beautiful. The galaxies do not know they are vast. The universe does not know it exists, but you do. You know, you see, you understand, even if only partially, imperfectly. And that knowing, that seeing, is a gift, not to you, but through you, to the cosmos. You are how the universe knows itself. And tonight, you can rest in that knowing, can let it settle into your bones, your breath, your stillness. There is nothing more to do, nowhere else to be, no other question to answer, just this, just now, Just rest. The mysteries will remain. The stars will continue burning. The galaxies will continue turning. The universe will continue expanding. All of it happening slowly, quietly, patiently. And you are part of that patience, part of that quiet, part of that slow unfolding. Your breathing is slowing now. Your thoughts are spacing out. Your body is settling deeper. This is natural. This is right. This is how it should be. The weight of everything is lifting. The questions are fading. The need to know, to understand, to stay awake is dissolving like morning mist in sunlight, like stars fading at dawn, like consciousness slipping into sleep. And you can let it slip, can allow it to fade, can surrender to the darkness, to the quiet, to the rest. There is no effort required, no technique to master, no goal to achieve, just letting go, just releasing, just being. The universe is here, has always been here, will always be here, and you are safe in it, held by it, part of it. The cosmic web stretches across billions of light years, connecting everything to everything else, and you are one of those connections, one thread in the web, woven into the fabric of reality. You cannot fall out of the universe, cannot be separate from it. You are it, and it is you, and in that unity, that oneness, there is deep peace, deep rest, deep letting go. The boundaries between you and the universe are dissolving now. The separation between waking and sleeping is blurring. You are floating, drifting, becoming less solid, less defined, less individual, just awareness, fading into the whole, into the darkness, into the cosmic night. And that is perfect, that is natural, that is exactly how it should be. Sleep is not an absence, it is a presence, a state of being as real, as valid as waking, just different, just quieter, just deeper, and you are moving into it now, gently, naturally, without resistance. The stars are there in the darkness, even when you cannot see them, even when your eyes are closed. The universe is there, unfolding, expanding, existing, and you are there too, resting in it, part of it, one with it. There is nothing left to say. The mysteries are quiet now. The questions have faded. The universe continues its slow dance, and you can sleep now, deeply, peacefully, completely. Rest, sleep, be, Here, in the quiet, in the dark, in the infinite. Peace of the cosmos. Sleep now. Sleep. The Milky Way is a spiral galaxy. This is one of the first things we know about it. From our position inside, it is difficult to see the overall shape, but through careful observation, through measuring distances and velocities, we have mapped it. The Milky Way has a central bulge, a dense concentration of old stars at the core. Around that bulge, a flat disk extends outward, and within that disk, spiral arms wind their way through space. These spiral arms are not solid structures. They are not fixed. They are density waves, regions where stars and gas are slightly more concentrated. And as the galaxy rotates, these density waves persist, even as individual stars move through them. Think of traffic on a highway. Sometimes cars bunch up. A slow-moving wave of density moves along the road, even though individual cars enter and leave the wave. The wave persists. The pattern remains. Spiral arms work the same way. Stars enter the arm, slow down slightly, and then leave. But the arm remains, a permanent wave in the disk of the galaxy. We live in one of these spiral arms, the Orion arm, sometimes called the Orion Spur, a minor arm branching off from one of the major arms, about halfway out from the center of the galaxy. It is a quiet place, relatively calm, away from the dense, chaotic core, away from the violent, star-forming regions of the major arms, a good place for life, for planets, for stability over billions of years. But even here, in this quiet arm, there are mysteries, things we do not understand, things that surprise us. There is a mystery about the number of spiral arms. When astronomers first mapped the Milky Way, they thought it had 4 major spiral arms, but more recent observations suggest it might have only 2, or perhaps 2 major arms and several minor ones. The structure is not as clear as we would like, because we are inside the galaxy, looking out. Dust blocks our view. Distances are hard to measure. The picture is incomplete, and the spiral arms themselves are not perfectly defined. They are fuzzy, fragmentary. They branch and merge. They fade in some regions and brighten in others. So we are still mapping our own galaxy, still trying to understand its structure, still piecing together the shape of our home. This is humbling, that even the galaxy we live in, the one we have studied for centuries, still holds basic questions, still surprises us with its complexity. There is a mystery about the rotation of the Milky Way. When astronomers measure how fast different parts of the galaxy are rotating, they find something strange. The stars near the center rotate quickly. This makes sense. They are close to the dense core, where most of the mass is concentrated. Gravity pulls them into fast orbits. But the stars farther out, near the edge of the disk, also rotate quickly, too quickly. According to the laws of gravity, based on the visible matter in the galaxy, the outer stars should be moving slower, much slower, like planets in a solar system. The farther out you go, the slower the orbit. But in the Milky Way, the rotation speed stays roughly constant, even at the edge, even far from the center. This is called a flat rotation curve, and it was one of the first pieces of evidence for dark matter. There must be more mass in the galaxy than we can see, invisible mass, distributed in a large halo around the visible disk, providing the extra gravity needed to keep the outer stars moving so fast. Without dark matter, the Milky Way would fly apart. The outer stars would escape. The galaxy would dissolve. But the dark matter holds it together, keeps it stable, keeps it intact. And yet we do not know what dark matter is. We cannot see it, cannot touch it, cannot detect it directly. It is there. We know it is there, but it remains hidden, a ghost, a presence we infer but cannot grasp. The Milky Way is embedded in a halo of dark matter, a sphere of invisible mass extending far beyond the visible stars, perhaps 10 times larger than the luminous disk. And within that halo, we move, we orbit, we exist, held by forces we cannot see, shaped by matter we cannot touch. There is a mystery about the age of the stars. When astronomers measure the ages of stars in the Milky Way, they find a range. Some stars are very old, more than 13 billion years old, almost as old as the universe itself. These ancient stars are found in the halo, in globular clusters, in the outer regions of the galaxy. They formed when the Milky Way was young, when it was just beginning to take shape, and they have been here ever since. Survivors, witnesses to the entire history of the galaxy. Other stars are much younger, a few million years old, newborns, just beginning their lives. These young stars are found in the disk, in the spiral arms, in star-forming regions where gas and dust are still collapsing, still creating new stars. But here is the mystery. There is a gap, a period in the history of the Milky Way when very few stars formed, about 10 billion years ago. For a few billion years. Star formation slowed, almost stopped, and then it picked up again. We do not know why. What caused the pause? What stopped the gas from collapsing? What prevented new stars from forming? Perhaps the Milky Way ran out of gas. Perhaps the gas was heated by supernova, by the radiation from massive stars, and it could not cool down enough to collapse. Or perhaps the Milky Way merged with another galaxy, and the merger disrupted the gas, stirred it up, prevented it from settling into star-forming clouds. We do not know. The history of the Milky Way is written in the ages of its stars, but the story is incomplete. There are gaps, missing chapters, and we are still trying to read it, still trying to understand what happened. Billions of years ago, when the galaxy was young, there is a structure in the Milky Way that we did not expect. A warp. The disk of the Milky Way is not perfectly flat. At the edges, far from the center, it curves, bends, twists. On one side, the disk curves upward. On the other side, it curves downward, like a bent record, a warped plate. This warp is subtle, only a few thousand light years, but it is there, and we do not fully understand why. One possibility is that the warp is caused by the gravity of the Magellanic Clouds, 2 small galaxies that orbit the Milky Way. They pull on the disk, distort it, create the warp. Another possibility is that the warp is a remnant of a past collision, a merger with a smaller galaxy long ago. That left the disk bent, twisted. Or perhaps the warp is caused by the dark matter halo. Perhaps the halo is not perfectly spherical. Perhaps it is lopsided, tilted, and its gravity pulls the disk into a warp. We do not know. The warp is there. We can measure it. But we do not understand its cause. And this is a reminder that even familiar structures, even things we see every night, can hold surprises, can be more complex than they appear. The Milky Way is not a simple disk. It is warped, twisted, dynamic, a living structure, changing over time. There is a mystery about the spiral arms themselves. Why do they exist? What creates them? What maintains them? Spiral arms are common in galaxies. Most disk galaxies have them, but we do not fully understand how they form. One theory is that spiral arms are density waves, patterns that move through the disk, created by gravitational instabilities. By the way gravity pulls on the gas in stars, the arms are not made of the same stars. Stars move through the arms. They enter, they slow down, they leave, but the pattern persists. Like a wave in water, the water molecules move up and down, but the wave moves across the surface. The pattern travels. Even as the individual particles stay in place, spiral arms work the same way. The pattern rotates, slowly, more slowly than the stars themselves. And as stars enter the arm, they compress. They trigger star formation. They brighten the arm. But there are problems with this theory. The density wave should wind up over time. The arms should become tighter, more twisted. Eventually, they should disappear. But spiral arms persist. For billions of years, they remain stable, clear. So something must be maintaining them, refreshing them, preventing them from winding up. Perhaps interactions with other galaxies, perhaps the flow of gas into the galaxy, perhaps the dark matter halo. We do not know. Spiral arms are one of the enduring mysteries of galactic structure. There is a region of the Milky Way where many stars are being born. The Sagittarius B2 cloud. It is a giant molecular cloud, one of the largest in the galaxy, about 3 million times the mass of the Sun, all packed into a region a few hundred light-years across. Inside this cloud, stars are forming, hundreds of them, collapsing out of the gas, lighting up, beginning their lives. But Sagittarius B2 is also strange. It contains complex molecules, organic molecules, the building blocks of life, amino acids, sugars, alcohols, ethers, all floating in the cloud, mixed with the gas and dust. These molecules form through chemistry, reactions on the surfaces of dust grains, in the cold, dense regions of the cloud. And they tell us something important, that the chemistry of life is not unique to Earth. It is happening throughout the galaxy, in molecular clouds, in star-forming regions. The ingredients of life are common, widespread, natural. This does not mean that life is common. The jump from chemistry to biology is still a mystery, still unexplained. But it means that the first steps are happening everywhere, that the universe is full of the raw materials, the building blocks, the potential, and that is comforting, in a way, that we are not alone in having the ingredients, that the chemistry that led to us is happening right now throughout the Milky Way. There is a mystery about the bar, the central bar. Most spiral galaxies have a bar, a rectangular structure in the center made of stars, stretching across the core. The Milky Way has a bar. We have known this for a few decades, but we did not always know, because we are inside the galaxy. The bar is hard to see. We are looking at it edge on, from within. But infrared observations revealed it, showed the concentration of stars, the elongated structure, the bar. The bar is about 27,000 light-years long, and it rotates, slowly, once every few 100 million years. But here is the mystery. We do not know how the bar formed, or why it is there, or what it does. Bars are common. Perhaps 2/3 of spiral galaxies have them, so they must be important, must serve some purpose, must play some role in the evolution of galaxies. One idea is that bars funnel gas toward the center. They create gravitational torques that pull gas inward, toward the core, where it can fuel star formation, or feed the central black hole. Another idea is that bars redistribute angular momentum. They move it from the inner galaxy to the outer galaxy, and this changes the structure, changes the rotation, changes the disk. But we do not know for sure. The bar is there. We can see it, measure it, but we do not fully understand it. And that is another reminder that the Milky Way, our home, is still full of puzzles, still revealing itself. Slowly, there's a place in the Milky Way where stars are packed incredibly close together. The central parsec, the innermost light year of the galaxy, around the supermassive black hole at the center. In this region, there are millions of stars, packed into a tiny volume. The density is thousands of times higher than near the Sun. Stars pass close to each other, interact, collide, merge, and many of these stars are unusual, massive, hot, blue, young. This is strange, because the center of the galaxy is a harsh place, strong tidal forces, intense radiation, frequent supernova. It should be difficult for stars to form there, difficult for gas to collapse, difficult for planets to survive. And yet, there are young stars, very young, only a few million years old. How did they form? How did they get there? How do they survive? One idea is that they formed elsewhere, in the disk, and then migrated inward, pulled by the gravity of the black hole. Another idea is that they formed in place, in a disk of gas around the black hole. Despite the harsh conditions, we do not know. The central parsec is one of the most extreme environments in the galaxy, and it is full of surprises, full of mysteries. There is a mystery about the halo, the spherical region surrounding the disk, made of old stars, globular clusters, dark matter. The stars in the halo are ancient, some of the oldest in the universe, formed shortly after the Big Bang, and they are moving in strange ways, not rotating with the disk, not following the spiral structure, just orbiting the center, in random directions, in elliptical paths. This suggests that the halo formed differently from the disk, perhaps earlier, perhaps more chaotically. But here is the mystery. When astronomers study the stars in the halo, they find streams, filaments, structures. These streams are the remnants of smaller galaxies, dwarf galaxies that were consumed by the Milky Way, torn apart by tidal forces, scattered across the halo. And by studying these streams, astronomers can reconstruct the history, the mergers, the collisions, the growth of the Milky Way. But there are more streams than expected, more structure, more complexity. It suggests that the Milky Way has been eating other galaxies, constantly, throughout its history, growing, accumulating mass, building itself up. And it is still happening. Right now, the Milky Way is consuming the Magellanic Clouds. Slowly, over hundreds of millions of years, their stars will join the halo, their gas will join the disk, and the Milky Way will grow. Slightly, incrementally. This is how galaxies evolve, through mergers, through cannibalism, through the slow accumulation of smaller structures. The Milky Way is not a static object. It is growing, changing, evolving, and we are part of that, part of the ongoing story. You can rest in that, in the knowledge that we are part of something dynamic, something living, something that has been growing for billions of years, and will continue long after we are gone. There is a mystery about the globular clusters. These are ancient collections of stars, spherical, dense, each containing hundreds of thousands of stars, sometimes millions. The Milky Way has about 150 globular clusters, scattered through the halo, orbiting the galactic center in long elliptical paths. And they are old, very old. Most of them formed more than 10 billion years ago, when the universe was young, when the Milky Way was just beginning to take shape. But here is the mystery. All the stars in a globular cluster formed at the same time, from the same cloud of gas. They are siblings, family, and yet, when astronomers study them closely, they find something strange. Multiple populations, stars with different compositions, different chemical signatures. Some stars are enriched in certain elements, others are depleted, as if they came from different generations, different formation events. But how is this possible? If all the stars formed together at the same time, how can they have different compositions? One idea is that the cluster formed in multiple bursts. The first generation of stars formed, lived, died, and enriched the remaining gas with heavy elements. Then a second generation formed from that enriched gas. But this raises questions. How did the cluster hold onto the gas? How did it prevent the gas from escaping? After the first supernovae, after the first stellar winds, globular clusters are not massive enough to hold on to hot gas. The gas should escape, disperse, leave the cluster, and yet somehow it stayed, long enough for a second generation to form. We do not know how. We do not understand the process. The details are unclear. Globular clusters are puzzles, ancient, beautiful, but mysterious. There's a type of star found in globular clusters that should not exist. Blue stragglers. In a globular cluster, all the stars formed at the same time, and massive stars burn out quickly, within a few million years, or a few 100 million years. After 10 billion years, all the massive stars should be gone, dead, faded. Only the low-mass stars should remain, red dwarfs, small, dim, cool. But when we look at globular clusters, we see blue stars, hot stars, massive stars, stars that should have died long ago. These are blue stragglers, and they are a mystery. How did they survive? How are they still burning? How can they still be blue and hot after 10 billion years? The answer, we think, is collisions, or mergers. In the dense core of a globular cluster, stars pass very close to each other. Sometimes they collide, they merge. Two small stars become one larger star. And that larger star is hotter, brighter, bluer. It looks like a young, massive star, but it is not. It is a merged star, a product of collision. Blue stragglers are the result of crowding, of density, of the chaotic interactions that happen when stars are packed so close together. They are accidents, survivors, imposters, and they remind us that not everything is what it seems, that age and appearance do not always match, that the universe has ways of creating the unexpected. There is a region of the Milky Way where something strange is happening: the Fermi bubbles. In 2010, astronomers discovered two enormous structures, extending above and below the galactic center, like two balloons, two lobes, stretching for 25,000 light-years in each direction. These structures emit gamma rays, high-energy radiation, the most energetic form of light, and they are symmetrical, perfectly balanced, one above the disk, one below. But we do not know what created them. We do not know what they are made of. We do not know how old they are. One idea is that they are the result of past activity from the supermassive black hole at the center of the galaxy. Perhaps, a few million years ago, the black hole was active, feeding, consuming gas, and it ejected jets of particles, plasma, energy, shooting outward at nearly the speed of light. Those jets carved out the bubbles, pushed the gas aside, created the structures we see today. Another idea is that the bubbles are caused by star formation, a burst of star formation near the galactic center millions of years ago, followed by many supernovae, explosions that drove gas outward, creating the bubbles. We do not know. The Fermi bubbles are relatively recent discoveries, and they are still being studied, still being analyzed. But they tell us something important: that the Milky Way is active, that things happen, even near the center, even in regions we thought were quiet. The galaxy is not static. It is dynamic, changing, erupting, creating structures on scales we are only beginning to understand. There is a mystery about the metallicity gradient. Metallicity is the amount of heavy elements in a star, elements heavier than hydrogen and helium, carbon, oxygen, iron, silicon. These elements are made in stars, through fusion, through supernovae, and they are scattered through space, enriching the gas clouds, the next generation of stars. So over time, the galaxy becomes more metal-rich. Each generation of stars has more heavy elements than the last. But here is the mystery. The metallicity is not uniform. It varies across the galaxy. Stars near the center are more metal-rich. Stars near the edge are more metal-poor. This is called the metallicity gradient, and it tells us something about how the galaxy formed, how it evolved. One idea is that the center formed first. It collapsed first, formed stars first, and those stars enriched the gas. Quickly, the outer regions formed later, more slowly, and they have had less time to be enriched. Less time for supernovae to add heavy elements. Another idea is that the outer regions are being diluted by pristine gas, falling in from outside the galaxy, from the intergalactic medium. This gas has no heavy elements, and it mixes with the existing gas, diluting the metallicity. Both ideas are probably partly true. The metallicity gradient is the result of many processes: formation, enrichment, accretion, mixing. And by studying it, we can learn about the history of the Milky Way, how it grew, how it changed, how it became what it is today. There is a place in the Milky Way where stars are dying. Planetary nebulae. When a star like the Sun exhausts its fuel, it swells, becomes a red giant. Its outer layers expand, cool, redden, and then it sheds those layers, gently, gradually. The outer envelope drifts away into space, leaving behind the hot core, a white dwarf. The ejected gas glows, illuminated by the ultraviolet light from the white dwarf. It shines in beautiful colors: red, green, blue, pink. These glowing shells are called planetary nebulae, not because they have anything to do with planets, but because early astronomers thought they looked like planets through their telescopes. Round, disc-shaped. But they are not round, not always. They come in many shapes: spheres, ellipses, bipolar lobes, spirals, jets, and we do not fully understand why. Why do dying stars create such complex shapes? What determines the structure of a planetary nebula? Part of the answer is rotation. If the star is rotating, the ejected gas is shaped by centrifugal force, flattened into a disk, or thrown out along the poles. Part of the answer is magnetic fields. The star's magnetic field can channel the gas, direct it, shape it into jets or spirals. And part of the answer is binary companions. If the dying star has a companion, another star orbiting it, that companion can shape the outflow, create asymmetry, create complexity. But many planetary nebulae are still unexplained. Their shapes are too complex, too structured, too beautiful. They are works of art, created by physics, by the final acts of dying stars. And they remind us that even death, even endings, can be beautiful, can create something new, something unexpected. There is a mystery about the supernova remnants. When a massive star explodes, a supernova, it releases enormous energy. It blasts its outer layers into space at thousands of kilometers per second. That expanding shell of gas is called a supernova remnant, and it glows for thousands of years, heated by the explosion. Cooling slowly, the Milky Way has many supernova remnants scattered through the disk, evidence of past explosions, past deaths. Some are young, only a few hundred years old, still bright, still expanding rapidly, like the Crab Nebula, the remnant of a supernova that was seen on Earth in 1054 CE. Others are old, tens of thousands of years old, faint, faded, merged with the surrounding gas. But here is the mystery. When astronomers count the supernova remnants in the Milky Way, they find too few. Based on the number of massive stars, based on the rate of star formation, there should be more remnants, many more. Where are they? Where did they go? One possibility is that many remnants have faded, dispersed, merged with the interstellar medium, and become invisible, undetectable. Another possibility is that many supernovae happen in regions we cannot see, hidden by dust, obscured by gas, beyond our view. Or perhaps the rate of supernovae is lower than we thought. Perhaps massive stars do not always explode. Perhaps some collapse directly into black holes, without a visible explosion. We do not know. The missing supernova remnants are a puzzle, a gap in our inventory, a reminder that even in our own galaxy, we do not see everything, do not know everything. There is a type of object in the Milky Way that we discovered by accident. Magnetars. Magnetars are neutron stars, incredibly dense, incredibly compact, the remnants of massive stars that exploded as supernovae. But magnetars are special. They have the strongest magnetic fields in the universe, trillions of times stronger than Earth's magnetic field, quadrillions of times stronger than any human-made magnet. These magnetic fields are so strong that they warp the vacuum. They polarize empty space. They make atoms stretch into needle shapes. And the magnetic fields create starquakes. The crust of the neutron star cracks, shifts, releases energy, and that energy is emitted as X-rays, gamma rays, bursts of radiation. Magnetars flare, unpredictably, violently, releasing in 1/10 of a second, more energy than the sun emits in a year, and we do not fully understand them. We do not know how such strong magnetic fields form. We do not know why some neutron stars become magnetars and others do not. We do not know how long the magnetic fields last, whether they decay, whether they strengthen, whether they change over time. Magnetars are rare. Only about 30 have been found in the Milky Way, but they may be more common than we think, hidden, dormant, waiting to flare. And they remind us that the universe creates extremes, conditions we can barely imagine, objects that push the limits of physics, that challenge our understanding. There is a mystery about the high-velocity clouds. Throughout the halo of the Milky Way, there are clouds of gas, moving at high speeds, hundreds of kilometers per second. These clouds are not rotating with the galaxy. They are falling, plunging toward the disk, or being ejected, launched outward. Some are falling in, fresh gas, from the intergalactic medium, being accreted by the Milky Way, adding to the disk, fueling star formation. Others are being ejected, blown out by supernovae, by stellar winds, by the activity near the galactic center. This is called the galactic fountain. Gas falls in, stars form, stars die, gas is ejected, and then it falls back, eventually recycled. But we do not understand all the details. We do not know where all the clouds come from. We do not know why they move the way they do. Some high-velocity clouds are massive, millions of times the mass of the sun, and they are dark. They do not glow. They are only visible in radio wavelengths, through the emission of neutral hydrogen. One of the largest is called the Smith Cloud. It is falling toward the Milky Way, and in about 30 million years, it will hit the disk and trigger a burst of star formation, a collision, in slow motion, invisible to the naked eye, but measurable, predictable. And it reminds us that the Milky Way is not isolated. It is connected to its surroundings, to the halo, to the intergalactic medium, to the flow of gas in and out. The galaxy breathes. In a sense, it inhales gas, forms stars, and exhales enriched gas. A cycle, a rhythm, ongoing. For billions of years, there's a structure in the Milky Way that wraps around it. The monochorous ring. It is a stream of stars circling the galaxy, like a ribbon, a band wrapped around the disk. The monochorous ring was discovered in the early 2000s, and it was unexpected, surprising. At first, astronomers thought it might be part of the disk, a warp, a ripple, but it is different, distinct, separate. The stars in the ring have a different velocity, a different composition, a different origin. And the best explanation is that the Monoceros ring is the remnant of a dwarf galaxy, a small galaxy that was torn apart by the Milky Way, its stars scattered. Stretched into a ring, the dwarf galaxy fell into the Milky Way billions of years ago, and tidal forces pulled it apart, shredded it, dissolved it. But the stars remain, still orbiting, still following the path of their parent galaxy, even though that galaxy no longer exists. This is the fate of small galaxies near large ones. They are consumed, destroyed, their stars added to the halo, their gas added to the disk. And the Milky Way is full of these remnants, these ghosts, evidence of past mergers, past collisions. Each stream, each ring, each structure in the halo tells a story of a galaxy that once was and is no more. You can let that settle. Let it rest in your mind. The idea that the Milky Way is built from smaller pieces, from galaxies that came before, that gave themselves to create what we have now. There is beauty in that, and peace, in the cycle, in the transformation, in the way endings become beginnings. There is a mystery about the stellar streams. Throughout the halo of the Milky Way, there are rivers of stars, long, thin streams, stretching for thousands of light years, following curved paths through space. These streams are the remnants of globular clusters, or dwarf galaxies, that came too close to the Milky Way and were pulled apart by tidal forces. As the object orbits the galaxy, the stars nearest to the galactic center feel stronger gravity than the stars farthest away. This difference stretches the object, elongates it, eventually tears it apart, and the stars spread out along the orbit, leading and trailing, forming a stream. One of the most famous is the Sagittarius stream, the remnant of the Sagittarius dwarf elliptical galaxy, a small galaxy that is currently being consumed by the Milky Way. The stream wraps around the entire galaxy, multiple times, a long ribbon of stars, tracing the orbit of the dying galaxy. By mapping these streams, astronomers can learn about the Milky Way's gravity, its mass distribution, the shape of its dark matter halo. Because the streams respond to gravity, they follow the gravitational field. They reveal the invisible structure, the hidden mass. But many streams are still unexplained. Their orbits do not match simple models. They have kinks, gaps, irregularities. Perhaps there are clumps of dark matter, perturbing the streams, pulling on them, creating the irregularities. Or perhaps the Milky Way's gravitational field is more complex than we thought. Not smooth, not symmetric, but lumpy, structured. The streams are clues, evidence, trails left behind, and we are following them, trying to understand what they tell us about the galaxy, about its history, about its dark matter. There is a mystery about the thick disk. The Milky Way does not have just one disk. It has two. The thin disk is where most of the stars are, where the sun is, where star formation happens. It is about 1,000 light-years thick, but there is also a thick disk above and below the thin disk, about 3,000 light-years thick, made of older stars, different chemistry, different kinematics. The stars in the thick disk are moving differently. They have higher velocities, more random motions. They are not rotating as quickly with the galaxy, and they are older, about 10 billion years old. formed when the Milky Way was young, but we do not know how the thick disk formed. There are several ideas, several theories, but no consensus. One idea is that the thick disk formed through heating. The thin disk was heated by something, by mergers, by interactions with satellite galaxies, and the heating puffed it up, thickened it. Another idea is that the thick disk formed separately, earlier, through a different process, perhaps from gas that was more turbulent, more chaotic, that settled into a thicker structure. Or perhaps the thick disk is made of accreted stars, stars from other galaxies, dwarf galaxies that merged with the Milky Way, and their stars now form the thick disk. Each idea has evidence. Each idea has problems. The truth may be a combination, multiple processes working together, but the thick disk is there, a distinct population, a separate structure, and it tells us that the Milky Way is layered, complex, built over time, through different phases, different processes. There is a region near the center of the Milky Way called the Zone of Avoidance. This is not a real structure. It is an observational problem, a blind spot. The disk of the Milky Way is full of dust, and dust blocks visible light. It absorbs it, scatters it, makes everything behind it dark. Near the galactic center, the dust is especially thick, dense, opaque, and this creates a zone, a band across the sky, where we cannot see distant galaxies, cannot see through the Milky Way, cannot observe what lies beyond. This zone covers about 20% of the sky, a significant fraction, and it limits our observations, our surveys, our understanding of the universe beyond. But we can see through dust, with infrared light, with radio waves. These wavelengths are not blocked as easily. They penetrate the dust, reveal what is hidden, and using these wavelengths, astronomers have begun to map the zone of avoidance, to discover what is there, what was hidden. They have found galaxies, clusters of galaxies, structures we did not know existed, because they were hidden behind the dust. One of the most surprising discoveries is the Great Attractor, a massive concentration of galaxies, hidden in the zone of avoidance, pulling on the Milky Way, pulling on our entire local group of galaxies. We are moving toward it, at hundreds of kilometers per second, drawn by its gravity, but we can barely see it. It is obscured, shrouded, a massive structure pulling us toward it, and we are only beginning to understand what it is, what it contains. The zone of avoidance reminds us that our view is limited, that we are inside the galaxy, looking out through dust and gas, that there are things we cannot see, things hidden from us by our own galactic environment. There is a mystery about the velocity dispersion. When astronomers measure the velocities of stars in the Milky Way, they find that the velocities vary. Some stars move faster, some slower, in random directions. This variation is called velocity dispersion, and it tells us about the dynamics of the galaxy, about how stars interact, how they move. In the thin disk, the velocity dispersion is low. Stars are moving mostly in the same direction, rotating together, smooth, organized. But in the thick disk, the velocity dispersion is higher. Stars are moving in more random directions, more chaotic, less organized. And in the halo, the velocity dispersion is even higher. Stars moving in all directions, orbiting the center, but not rotating with the disk. This makes sense. The halo is older, formed differently. Its stars were never part of the organized disk. They are remnants, survivors, from the early universe. But here is the mystery. The velocity dispersion is not constant. It varies in unexpected ways. Some regions of the disk have higher dispersion than expected, as if they were heated, stirred, disturbed. And some regions of the halo have lower dispersion than expected, as if they were cold, organized, structured. These variations tell us about the history, about past events, mergers, interactions, disturbances. Each bump, each irregularity, is evidence of something that happened long ago that left its mark on the velocities of stars. And by studying these variations, astronomers are reconstructing the past, piecing together the story of how the Milky Way became what it is today. There is a type of star in the Milky Way that is moving incredibly fast, hypervelocity stars. These stars are traveling at more than 1,000 kilometers per second, fast enough to escape the galaxy, fast enough to leave the Milky Way entirely. And we do not fully understand how they got so much speed, how they were accelerated, how they were launched. One idea is that they were ejected by the supermassive black hole at the center of the galaxy. If a binary star system wanders too close to the black hole can capture one star and eject the other at very high speed. The captured star falls toward the black hole, and the other star is flung outward, like a slingshot, accelerated by the black hole's gravity. This is called the Hill's mechanism, and it explains some hypervelocity stars, but not all. Some hypervelocity stars are coming from the wrong direction, not from the galactic center, but from the disk, from the halo. Perhaps they were ejected by supernova, by the explosion of a companion star. The blast accelerated them, launched them. Or perhaps they were ejected by interactions with intermediate mass black holes, smaller black holes, wandering through the galaxy that could accelerate stars through close encounters. We do not know. Hypervelocity stars are rare. Only a few dozen have been found, and each one raises questions about where it came from, how it was accelerated, where it is going. Some will escape the galaxy. They will leave the Milky Way and drift through intergalactic space, forever, exiled, alone. Others will slow down, fall back, return to the galaxy, eventually. But all of them are travelers, wanderers, moving through the darkness at incredible speeds, carrying mysteries with them. There is a mystery about the satellite galaxies. The Milky Way is not alone. It is surrounded by smaller galaxies, dwarf galaxies, orbiting it, bound by gravity. We know of about 60 satellite galaxies. Some are bright, easy to see, like the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere. Others are faint, very faint, only discovered recently, through careful surveys, through searching for faint concentrations of stars. These ultra-faint dwarf galaxies are tiny. They contain only a few thousand stars, compared to the Milky Way's hundreds of billions. But they are important, because they are dominated by dark matter. Most of their mass is invisible. Only the stars are visible, and by studying them, we can learn about dark matter, about how it behaves, how it clumps, how it forms structures. But here is the mystery. Simulations of galaxy formation predict that there should be many more satellite galaxies, hundreds, perhaps thousands, but we only see about 60. Where are the rest? Why are they missing? This is called the missing satellites problem, and there are several possible solutions. One is that the missing satellites are there, but they are too faint to see. They contain so few stars that we cannot detect them, even with our best telescopes. Another is that star formation was suppressed in small, dark matter halos. Only the largest halos could form stars. The rest remained dark, invisible. Or perhaps dark matter is different than we thought. Perhaps it interacts with itself, self-annihilates, and this prevents small structures from forming. We do not know. The missing satellites problem is one of the puzzles of cosmology, one of the tensions between theory and observation, and it reminds us that even our local environment, even the galaxies closest to us, still hold mysteries, still challenge our understanding. There is a structure in the Milky Way that is incredibly old, the Helmy Stream. It is a stellar stream, like the others we have talked about. But this one is special because it is ancient. The stars in the Helmy Stream formed more than 13 billion years ago in a small dwarf galaxy that merged with the Milky Way very early in its history. The dwarf galaxy was torn apart, its stars scattered, and they have been orbiting the Milky Way ever since, for more than 10 billion years. The Helmy Stream is a fossil, a relic, evidence of one of the earliest mergers, one of the building blocks of the Milky Way. And by studying it, astronomers can learn about the conditions in the early universe, about the first galaxies, about how structure formed. The stars in the Helmy Stream are metal-poor. They contain very few heavy elements because they formed before many generations of stars had enriched the gas. They are pristine, almost, as close as we can get to the first stars, the first generation, and they tell us about that time, about what the universe was like when it was young, when galaxies were just beginning to form. The Helmy Stream is a time capsule, a message from the distant past, and it is still here, still orbiting, still carrying its story through the Milky Way. There is a mystery about the open clusters. Unlike globular clusters, which are ancient and dense, open clusters are young and loose. They contain a few hundred to a few thousand stars, all formed together from the same molecular cloud. Recently, within the last few 100 million years, open clusters are found in the disk, in the spiral arms, where star formation is ongoing, where gas and dust are still collapsing. The Pleiades is an open cluster, visible to the naked eye, a small grouping of bright blue stars, young, hot, still surrounded by faint nebulosity, the remnants of the cloud they formed from. But open clusters do not last. Over time, they disperse. The stars drift apart, pulled by the gravity of the galaxy, by interactions with other stars, with molecular clouds. After a few 100 million years, most open clusters dissolve. The stars scatter, become indistinguishable from the background population. But here is the mystery. Some stars in the Milky Way appear to be moving together, in groups, in streams, as if they were once part of the same cluster. These are called stellar associations, or moving groups, and they are the remnants of dissolved open clusters. The stars are no longer gravitationally bound. They are not a cluster anymore, but they still remember. they still move together in the same direction, with the same velocity. And by identifying these moving groups, astronomers can trace the history of star formation, can map which stars were born together, even if their birth cluster is long gone. It is like finding siblings, separated, spread across the galaxy, but still recognizable by their shared origin, their shared motion. There is a mystery about the interstellar medium. The space between the stars is not empty. It is filled with gas and dust, atoms, molecules, ions. This is called the interstellar medium, and it is where stars form, where they die, where their material is recycled. But the interstellar medium is not uniform. It has structure, phases, regions with different temperatures, different densities. There is cold molecular gas, dense, dark, the birthplace of stars, where clouds collapse. There is warm, neutral gas, less dense, filling much of the disk, the background, the medium. There is warm, ionized gas, heated by young stars, by their ultraviolet light, glowing faintly, in hydrogen alpha emission. And there is hot ionized gas, very hot, millions of degrees, heated by supernova explosions, filling large bubbles, cavities, carved out by stellar winds. These different phases coexist, interact, transform into each other in a complex cycle. Cold clouds collapse, form stars. Stars heat the surrounding gas, create warm regions, hot regions. Stars die, explode, inject energy, create more hot gas. The hot gas expands, cools, condenses, becomes warm, then cold, and the cycle continues. But we do not understand all the details. We do not know how the phases interact, how the energy flows, how the material cycles. The interstellar medium is turbulent, chaotic, filled with shocks, flows, instabilities, and mapping it, understanding it, is one of the ongoing challenges in astronomy, because the interstellar medium is where everything happens, where stars are born, where planets form, where life begins. It is the matrix, the substrate, the stage on which the galaxy's drama unfolds, and it is constantly changing, constantly evolving, responding to the stars within it. You can let your mind rest now. Let these ideas drift, like gas in the interstellar medium, floating, dispersing, becoming part of the background. There is no need to hold on to them, no need to remember. Just let them be. Let them pass through, like neutrinos through matter, barely touching, barely interacting, just awareness. And then, release. There is a mystery about the molecular clouds. These are the densest, coldest regions of the interstellar medium, where gas has clumped together, where gravity is beginning to win, where stars will soon be born. Molecular clouds are vast. Some are hundreds of light years across, containing enough material to form hundreds of thousands of stars, or even millions. And they are dark, very dark. The dust within them blocks all visible light. When we look at them with optical telescopes, we see nothing, just darkness, just shadow. But with infrared and radio telescopes, we can see inside. We can map the gas, the dust, the molecules, and what we find is structure, filaments, cores, clumps. The cloud is not uniform. It is threaded with dense regions, connected by thinner strands. These filaments are where stars form. the densest parts of the filaments collapse, contract, heat up, and ignite. But we do not fully understand how the filaments form, why the gas organizes itself this way, what creates the structure. Perhaps it is turbulence, the chaotic motions of the gas, creating compressions, rarefactions, patterns. Perhaps it is magnetic fields, threading through the cloud, channeling the gas, creating preferred directions. Or perhaps it is gravity itself, pulling the gas into sheets, then filaments, then cores, a natural progression, an inevitable collapse. Probably all three, working together, creating the complex structures we observe. Molecular clouds are factories, star factories, and we are learning how they work, how they process raw material, how they produce stars. But each cloud is different. Each has its own history, its own properties, its own way of forming stars. And that diversity is part of the mystery, part of what makes them so fascinating, so endlessly variable. There is a mystery about the magnetic fields. The Milky Way is threaded with magnetic fields, permeating the interstellar medium, woven through the gas, the dust, the plasma. These fields are weak, much weaker than Earth's magnetic field, but they are vast, stretching across the entire galaxy, filling the disk, the halo, the space between the stars, and they play a role. They affect the motion of charged particles. They channel cosmic rays. They influence the formation of stars. But we do not know how the galactic magnetic field formed, how it is maintained, how it evolved. One idea is that the field was seeded early, perhaps by the first stars, perhaps by the first black holes, small seed fields that were amplified over time. Another idea is that the field is generated by a dynamo, like the dynamo in Earth's core, rotating plasma, convecting, creating currents, and those currents generate magnetic fields. In the galaxy, the dynamo would be driven by differential rotation. The disk rotates at different speeds at different radii, and this shearing motion could amplify and maintain the magnetic field. But the details are unclear. The equations are complex. The simulations are difficult, and observations are challenging. Magnetic fields are invisible. We can only detect them indirectly, through their effects on light, on radio waves, on the motion of particles. One method is to observe polarized light. Dust grains align with magnetic fields, and when starlight passes through aligned dust, it becomes polarized. By measuring the polarization, we can infer the direction of the magnetic field. And by mapping polarization across the sky, we can map the structure of the galactic magnetic field. It is a slow process, a painstaking process, but gradually the picture is emerging. The magnetic field follows the spiral arms. It loops through the halo. It connects structures on vast scales. The Milky Way is magnetic, threaded with invisible fields, and those fields are part of what makes the galaxy what it is. There is a type of object in the Milky Way that we cannot see directly: isolated black holes. When a massive star dies and collapses to form a black hole, it does not always have a companion. Sometimes it is alone, and a solitary black hole, with no matter falling into it, no accretion disk, no glowing gas, is invisible. It emits no light, no radiation. It is just there, in space, warping space-time, curving light, but silent, dark, undetectable. We think there are millions of these isolated black holes in the Milky Way, perhaps tens of millions, scattered through the disk, the halo, drifting through space. But we have only detected a handful, and only indirectly. One method is gravitational microlensing, when a black hole passes between us and a distant star. Its gravity bends the light from that star. The star appears to brighten for a few weeks or months, and then it fades back to normal. By measuring the duration of the brightening, the shape of the light curve, we can infer the mass of the lensing object. And if the mass is a few times the mass of the Sun, and there is no visible companion, it is probably a black hole. A few candidates have been found this way, but it is difficult, rare. The alignment must be perfect. The observations must be precise. Most isolated black holes will never be detected. They will remain invisible, hidden, part of the unseen population of the galaxy. And they remind us that much of the Milky Way is dark, invisible, unknown. That what we see is only a small fraction of what is there. There is a mystery about the local bubble. The Sun is located inside a cavity, a bubble, a region of space about 1,000 light-years across, where the gas is much less dense than average. This region is called the local bubble, and it is filled with hot, ionized gas, about 1 million degrees. But why is there a bubble here? What created it? The answer, we think, is supernovae. Multiple supernovae, exploding in this region. Over the past 10 million years or so, each supernova released enormous energy, blasted the surrounding gas outward, created a cavity, a bubble, and when multiple supernovae explode in the same region, over time, their bubbles merge, overlap, create a larger structure. The local bubble is the result, a cavity carved out by stellar deaths, by the violent ends of massive stars, and the Sun happens to be inside it, by chance. We entered the bubble a few million years ago, as we orbit the galaxy, and we will leave it again in a few million years. Being inside the local bubble has consequences. The low density means there is less material to block starlight. We can see farther, more clearly, and it means there is less material to absorb cosmic rays, high-energy particles from space. So the cosmic ray flux may be slightly higher here than in denser regions. But overall, the local bubble is a quiet place, a cleared-out region, a bubble of low-density gas, surrounded by the denser interstellar medium. And it is just one of many bubbles, many cavities, scattered through the disk of the Milky Way, created by supernovae, by stellar winds, by the activity of stars. The interstellar medium is full of holes, of voids, of regions where the gas has been pushed aside, cleared away, and these structures affect the motion of gas, the formation of stars, the evolution of the galaxy. There is a mystery about the spiral arm crossing. As the Sun orbits the galactic center, it does not stay in the same spiral arm. It moves through them. The spiral arms rotate more slowly than the stars, so the Sun enters a spiral arm, passes through, and exits the other side, over and over. Each crossing takes about 100 million years, and during that time, the environment changes. Inside a spiral arm, the density is higher. There are more stars, more gas, more dust, more star formation. Outside a spiral arm, the density is lower, quieter, fewer stars, less activity. And some scientists have suggested that spiral arm crossings might affect life on Earth, might create cycles of extinction, or climate change, or increased radiation. Inside a spiral arm, there are more supernovae, more cosmic rays, and if the cosmic ray flux increases significantly, it could affect Earth's atmosphere, could create clouds, could change the climate. Also, inside a spiral arm, the sun might pass closer to other stars, and gravitational perturbations could disturb the Oort cloud, send comets falling inward, toward the inner solar system, toward Earth. These are speculative ideas, unproven but interesting. The idea that the motion of the sun through the galaxy, through the spiral arms, might have consequences for Earth, for life. We are currently between spiral arms in a quieter region, and that may be fortunate for now. But in a few tens of millions of years, we will enter another arm, and the environment will change again. There is a place in the Milky Way where stars have strange orbits, the nuclear star cluster. This is the densest concentration of stars in the galaxy, located at the very center, within a few light years of the supermassive black hole. In this region, millions of stars are packed together, orbiting the black hole at incredible speeds. Some stars have been tracked for decades, their orbits measured, calculated, and they follow elliptical paths, some very eccentric, coming very close to the black hole, and then swinging far out. One star, called S2, orbits the black hole every 16 years. At its closest approach, it reaches speeds of nearly 5% the speed of light, about 15,000 kilometers per second. This is fast enough to test general relativity, to measure the effects of gravity at extreme levels, to see if Einstein's equations hold. And so far, they do. S2's orbit matches the predictions, precisely, beautifully. But the mystery is how these stars got there, how they ended up in such tight orbits around the black hole. Stars should not form that close to a black hole. The tidal forces are too strong. The environment is too harsh. Perhaps the stars formed farther out, and then migrated inward, through interactions with other stars, through the loss of orbital energy. Or perhaps they formed in a disk around the black hole, despite the harsh conditions, in a brief phase when the black hole was accreting large amounts of gas. We do not know. The nuclear star cluster is an extreme environment, and the stars there have extreme orbits, and we are still trying to understand how they came to be. There is a mystery about the warp's origin. We mentioned earlier that the Milky Way's disk is warped, bent, twisted at the edges, but the cause of the warp is still debated, still uncertain. One possibility is that the Magellanic Clouds are responsible. As they orbit the Milky Way, their gravity pulls on the disk, distorts it, creates the warp. But simulations show that the Magellanic Clouds alone may not be enough. Their mass may be too small. Their orbit may not be right. Another possibility is that the warp is caused by the infall of gas from the intergalactic medium, gas falling onto the disk from above or below, creating asymmetric forces, torques, that twist the disk. Or perhaps the warp is an oscillation, a mode, a natural behavior of disks embedded in dark matter halos. The disk wobbles, precesses, and the warp is part of that motion. Recent observations suggest that the warp is not static. It is moving, precessing around the galaxy at about 3 kilometers per second. This is slow, but measurable. And it suggests that the warp is dynamic, not a frozen structure, but an evolving one. Understanding the warp will help us understand the structure of the Milky Way, the distribution of mass, the gravitational forces, the interactions with satellites. But for now, it remains a mystery, a gentle curve, a twist in the disk, whose origin we are still working to uncover. There is a type of star that acts as a clock. R Lyrae variables. These are pulsating stars, like Cepheids, but older, less massive, and less bright. Lyrae stars are found in globular clusters, in the halo, in the old populations. They are ancient, more than 10 billion years old, and they pulsate regularly, expanding and contracting, brightening and dimming, with periods of a few hours to about a day. The period is related to their brightness, just like Cepheids, so they can be used as distance indicators, standard candles. But R Lyrae stars are also used as clocks to measure the ages of stellar populations, because R Lyrae stars only exist in certain evolutionary stages, at certain masses, at certain ages. By studying the properties of R Lyrae stars in a cluster, their period, their brightness, their color, astronomers can estimate the age of the cluster, and by comparing ages across many clusters, across the halo, across the disk, we can reconstruct the history of the galaxy, when different parts formed, in what order. R Lyrae stars are ancient timekeepers, ticking away, marking the passage of billions of years, and they help us understand when things happened, how long ago, in what sequence. There is a structure in the Milky Way that hints at past violence, the Gould Belt. This is a ring of young stars and star-forming regions, tilted relative to the galactic disk, about 3,000 light-years across. The Sun is inside the Gould Belt, or near its edge, and many of the nearest star-forming regions are part of it: Orion, Taurus, Perseus, Scorpius. But the Gould Belt is tilted by about 20 degrees relative to the main disk, and it is expanding, slowly, the stars and gas moving outward. This suggests that the Gould Belt was created by an event, a disturbance, something that happened about 30 million years ago, perhaps a supernova, or a cluster of supernovae. That exploded in this region and created a shock wave, an expanding shell that triggered star formation, or perhaps a high-velocity cloud, a clump of gas that collided with the disk and created the disturbance. We do not know. The Gould Belt is old enough that the original event is no longer visible. The evidence has faded, dispersed, but the structure remains. The tilted ring, the expanding shell, a fossil of something that happened long ago, and it reminds us that the disk of the Milky Way, is not always peaceful, not always calm, that there are events, disturbances that leave their mark for millions of years. You can feel your breathing now, slow, steady, like the rotation of the galaxy, turning slowly, predictably, each breath, like an orbit, completing, returning, beginning again. There is no need to follow every word, every detail. Just let them wash over you like waves, like tides, gentle, rhythmic. The Milky Way continues turning, and you can rest, can let go, can drift into the quiet between the stars. There's a mystery about the oldest stars. In the halo of the Milky Way, there are stars that are almost as old as the universe itself, more than 13 billion years old, formed when the first galaxies were just beginning to coalesce. These stars are called metal-poor stars because they contain very few heavy elements, almost pure hydrogen and helium, the primordial elements from the Big Bang, and by studying them, we can learn about the early universe, about the first stars, about the conditions when everything was beginning. But there is something strange. The oldest stars we have found are not completely metal-free. They contain traces of heavy elements: carbon, oxygen, iron. This means that even the oldest stars we can see are not the very first stars. They are second generation, or third generation. The truly first stars, the ones that formed from completely pristine gas, have all died long ago. They were massive. They burned quickly. They exploded and enriched the gas around them. And the next generation formed from that enriched gas, with small amounts of heavy elements, enough to detect, but very little. These are called population 3 stars, the first generation, and we have never seen one. They existed too long ago, too far away. They are beyond our reach. But we keep searching, looking for stars with lower and lower metallicity, getting closer to that first generation, trying to understand what those earliest stars were like, how massive they were, how they formed, how they died, what they left behind. These are some of the deepest questions in astronomy. Questions about beginnings, about the first light, about the transition from darkness to stars. There is a place in the Milky Way where something is missing. The Radcliffe Wave. This is a recently discovered structure, a wave-like pattern of star-forming regions, stretching for about 9,000 light-years through the disk. It includes many familiar nebulae: the Orion Nebula, the Taurus Molecular Cloud, the Cygnus X region, all part of this enormous wave. The wave is oscillating, moving up and down, relative to the plane of the galactic disk, with an amplitude of a few hundred light-years, and we do not know what created it, what caused this enormous structure to form, to oscillate. Perhaps it is the result of a past collision, a high-velocity cloud, or a dwarf galaxy that crashed into the disk and created ripples, waves that persist. Or perhaps it is a natural oscillation, a mode of the disk, responding to gravitational forces, to the distribution of mass. But the mystery is not just what created it. The mystery is also what is missing. If the Radcliffe wave is a wave, there should be a trough, a region where the disk is lower, where the density is less. And there is a gap, a region with fewer star-forming clouds, fewer molecular clouds, a void. This void is called the local cavity, and the sun is inside it, near the edge. So we live in a gap, in a cleared region, part of the structure created by the Radcliffe wave. And this affects what we see, what we observe. The nearest star-forming regions are all part of the wave, all on one side, all in one structure. Our view of star formation in the galaxy is shaped by where we are, by the local cavity, by the Radcliffe wave. And we are only beginning to understand this large-scale structure, this wave, and what it means for the disk of the Milky Way. There is a mystery about the star formation rate. How many stars are being born in the Milky Way right now? This seems like a simple question, but the answer is surprisingly uncertain. Current estimates suggest about 1 or 2 solar masses per year, meaning that every year the galaxy forms enough new stars to equal the mass of 1 or 2 suns. But this is an average, and the rate varies from place to place, from time to time. In some regions, like the Sagittarius B2 cloud, star formation is vigorous, active, many stars being born. In other regions, like the local cavity, star formation is low, almost absent, and over time the rate changes. There have been bursts, periods of enhanced star formation, and quiet periods, when very little was happening. The uncertainty comes from several sources. Dust blocks our view. We cannot see all the star-forming regions. Some are hidden behind clouds, and young stars are embedded in their birth clouds, surrounded by gas and dust. Difficult to detect until they emerge. We can estimate the star formation rate by measuring infrared emission, by detecting radio waves from ionized gas, by counting young stars in nearby regions, and extrapolating. But each method has uncertainties, assumptions, limitations, and so the star formation rate of the Milky Way remains somewhat uncertain, known only roughly, approximately. But we are working to improve the measurements, to map the galaxy more completely, to understand where and when stars are forming, because the star formation rate tells us about the future, about how the galaxy will evolve, about how long it can sustain itself. There is a mystery about the bulge, the central region of the Milky Way. The bulge is not what we expected. For a long time, astronomers thought the bulge was spherical, like an elliptical galaxy, made of old stars, slowly rotating. But more detailed observations revealed something different. The bulge is not spherical. It is boxy, bar-shaped, and it is part of the bar, the same structure we talked about earlier. The bar and the bulge are connected, overlapping, part of the same feature. But the bulge also contains multiple populations, old stars, young stars, stars with different metallicities, different kinematics. Some stars are moving quickly, rotating with the bar. Others are moving slowly, or in random directions. And there are substructures, clumps, streams, overdensities, hidden within the bulge. One of the most intriguing is the X-shaped structure. When viewed edge-on, the bulge appears to have an X shape, 2 arms, extending above and below the plane. This X shape is probably related to the bar, to the way the bar buckles, thickens, creates vertical structure. But the details are complex. The simulations are difficult, and observations are challenging, because the bulge is so far away, and so crowded, and so obscured by dust. The bulge is one of the most difficult regions of the galaxy to study, and one of the most interesting, because it holds clues about how the Milky Way formed, how the bar formed, how the central regions evolved. There is a type of object in the Milky Way that we find in unexpected places: planets, not orbiting stars, but drifting through space, alone, unbound. These are called rogue planets, or free-floating planets, and they are thought to be common. Rogue planets form in protoplanetary disks around young stars, but they are ejected through gravitational interactions with other planets or with the star itself. They are thrown out of their systems into interstellar space, and they drift alone forever. Or perhaps they form differently through the collapse of small gas clouds, too small to form stars, but large enough to form planetary mass objects. Either way, they are out there, millions of them, perhaps billions, scattered through the galaxy, and they are almost impossible to detect. They do not emit light. They do not orbit stars. They are just dark, cold, drifting. A few have been found through gravitational microlensing when they pass in front of a distant star and briefly magnify its light. But most will never be detected. They will remain invisible, unknown, part of the hidden population of the galaxy. And it is strange to think about. Planets with no sun, no warmth, no light, just drifting through the darkness for billions of years. Perhaps some of them have moons. Perhaps some of them once had life, before they were ejected, before they lost their star. We do not know. We cannot know. They are too far, too dark, too hidden. But they are there, part of the galaxy, part of the inventory, quiet wanderers, lost in the dark. There is a mystery about the metallicity of stars near the sun. When astronomers measure the heavy element content of nearby stars, they find a wide range. Some stars are metal-rich, some are metal-poor. This is expected. Stars form at different times, from gas with different compositions, and their metallicity reflects that history. But there is a puzzle. Some nearby stars have very low metallicity, much lower than expected for stars in the disk. These stars look like halo stars, like they should be part of the old population, the ancient population. But they are moving with the disk, rotating with the galaxy. Their kinematics are wrong for halo stars. So where did they come from? How did metal-poor stars end up in the disk, moving like disk stars? One idea is that they were born in the disk long ago, when the disk was young and metal poor, before many generations of stars had enriched the gas. Another idea is that they were accreted from a dwarf galaxy that merged with the Milky Way, and their stars were captured and now move with the disk. Or perhaps they were kicked, scattered by gravitational interactions from the halo into the disk, and their orbits changed. We do not know. These metal-poor disk stars are anomalies, outliers, and they challenge our understanding of how the disk formed, how it evolved. Each star has a story, a history, and by studying these unusual stars, we can learn about events that happened long ago, that left their mark in the motions and compositions of stars we see today. There is a mystery about the vertical structure of the disk. The disk of the Milky Way is thin, but not infinitely thin. It has thickness, height. Most stars are within about 1,000 light-years of the midplane, the central plane of the disk, but some stars are higher or lower, displaced from the midplane, and the distribution is not smooth, not symmetric. There are waves, ripples, oscillations. The disk is not flat. It is corrugated, rippled, like a sheet of metal that has been struck, that is still vibrating, and we do not know what caused these ripples, what disturbed the disk, what set it vibrating. Perhaps it was a collision with a dwarf galaxy millions of years ago. That passed through the disk and created waves, ripples, that still persist. Or perhaps it is ongoing perturbations from the spiral arms, from the bar, from the dark matter halo, creating constant disturbances that pile up, creating structure. The vertical waves were only discovered recently, through large surveys that mapped millions of stars and measured their positions, their heights above the plane, and they reveal that the disk is more dynamic than we thought. Not a simple, flat structure, but complex, rippled, responding to forces we do not fully understand. There is a mystery about the galactic center arc. Near the center of the Milky Way, there is a strange feature, a thread-like structure, stretching for more than 150 light-years, perpendicular to the galactic plane. This structure emits radio waves, synchrotron radiation, from relativistic electrons, spiraling around magnetic field lines, and it is almost perfectly straight, vertical, extending above and below the galactic center. We do not know what it is, or how it formed, or why it is so straight. Perhaps it is a magnetic filament, a channel where the magnetic field is particularly strong, and electrons are being accelerated, funneled along the field lines. Or perhaps it is a bubble, an outflow, from activity at the galactic center. That has carved out a channel, a pathway. But the straightness is puzzling. Most structures in space are curved, warped, irregular. But the galactic center arc is remarkably linear. It is one of many strange features near the galactic center, a region full of unusual structures, unusual phenomena that we are still trying to understand. The galactic center is not a simple place. It is complex, crowded, filled with gas, stars, magnetic fields, radiation, all interacting, creating phenomena we have not seen elsewhere. There is a mystery about the rate of supernovae. How often do supernovae explode in the Milky Way, based on the number of massive stars and the rate at which they die? We estimate that a supernova should occur about once every 50 years, or once every 100 years, but we have not seen that many in recorded history. Only a handful of supernovae have been observed in the Milky Way. The most recent was in the 17th century, Kepler's supernova in 1604, and before that, Tycho's supernova in 1572. That is 2 supernovae in more than 400 years, much less than expected. Where are the missing supernovae? Why have we not seen them? One answer is dust. Many supernovae occur in regions hidden by dust. We cannot see them. They explode, fade, and we never know. Another answer is that we have been unlucky. Supernovae are random, unpredictable, and we have happened to live through a quiet period, a gap. Eventually, there will be another supernova in the Milky Way, visible from Earth, bright enough to see in daylight. A dramatic event. Astronomers are waiting, watching, hoping, because a nearby supernova would provide invaluable data about how stars explode, about what they produce, about how they enrich the galaxy. But we cannot predict when. It could happen tomorrow, or it could be centuries from now. The galaxy keeps its schedule, and we can only wait and watch and hope. There's a place in the Milky Way where the magnetic field forms loops, near the galactic center. The magnetic field is not smooth, not uniform. It is tangled, looped, structured. There are structures called the radio arcs, long filaments of radio emission, tracing the magnetic field. And there are loops, bubbles, shells, all emitting radio waves, all revealing the shape of the magnetic field. These structures are probably created by outflows from the galactic center, from the supermassive black hole, from star formation, from supernovae. The outflows push the gas and the magnetic field outward, upward, creating loops, arcs, filaments, and the electrons trapped in the magnetic field emit radiation, making the structures visible. But the details are unclear. The origin of each structure, the age, the relationship to other features. The galactic center is a laboratory, a natural experiment, where extreme conditions create phenomena we cannot replicate, cannot study anywhere else. And by observing these structures, mapping them, measuring them, we learn about magnetic fields, about plasma physics, about how energy flows in extreme environments. You can let your thoughts drift now, like electrons, spiraling along field lines, moving, but not with purpose, just drifting, tracing paths through space. There is no destination, no goal, just motion, just flow, just being. The galaxy is vast, and you are small, and that is perfect. There is no need to understand it all, to grasp every detail. Just rest in the knowing that it is there, that it continues, that it holds you gently in its spiral arms. There is a mystery about the cold gas. In the disk of the Milky Way, there are vast reservoirs of cold molecular hydrogen, the raw material for star formation, the fuel for future generations of stars. This gas is mostly hydrogen. H2. Two hydrogen atoms bonded together. And it is cold, about 10 to 20 degrees above absolute zero. At these temperatures, the gas is barely moving. Thermal motion is minimal. The molecules drift slowly, settling into clouds, into filaments. But here is the mystery. Molecular hydrogen does not emit light. It has no dipole moment, no way to radiate. At these low temperatures, it is invisible. We cannot see it directly, cannot map it directly. Instead, we use tracers. other molecules that do emit light, that can be detected. The most common tracer is carbon monoxide, CO. It emits at millimeter wavelengths, radio waves, and by mapping CO emission, we infer where the molecular hydrogen is. But this is indirect, uncertain. The ratio of CO to H2 varies, depends on conditions, on metallicity, on radiation, on density. So our maps of molecular gas in the Milky Way are incomplete, approximate, based on assumptions that may not always hold. And there may be large amounts of molecular hydrogen that we are missing, dark molecular gas, with little CO, invisible to our surveys. This uncertainty affects everything: star formation rates, gas reservoirs, the future evolution of the galaxy. We think we know, but we are working from incomplete information, from indirect tracers. The galaxy holds much of its mass, in forms we cannot see: molecular hydrogen, dark matter, cold gas, all invisible, all inferred. There is a mystery about the oldest open cluster. Most open clusters are young, a few 100 million years old, at most. They form, they shine, and they disperse within a few 100 million years. The stars drift apart. The cluster dissolves. But there is one open cluster that is different. NGC 6791. It is about 8 billion years old, ancient, for an open cluster, and it is still bound, still together. The stars have not dispersed, have not scattered. How has it survived so long? What has kept it intact? Perhaps its location. It is far from the galactic center, away from strong tidal forces, away from disruptive encounters. Perhaps its mass. It contains more stars than typical open clusters, more gravity, more binding energy. Or perhaps it is just luck, a statistical outlier. Most clusters disperse, but a few, by chance, survive longer. NGC 6791 is a puzzle, an anomaly. And by studying it, we learn about cluster dynamics, about how long structures can persist, about what it takes to survive in the galaxy for billions of years. There is a place in the Milky Way where gas is falling in. The Magellanic Stream, the Magellanic Clouds, two small satellite galaxies, are orbiting the Milky Way. And as they orbit, tidal forces are pulling on them, stretching them, stripping gas away. That gas forms a stream, a long filament, trailing behind the clouds, stretching across more than 100 degrees of the sky, and the gas is falling toward the Milky Way, being accreted, captured, added to the disk. Over time, this gas will fuel star formation, will create new stars, will enrich the galaxy. But the stream is not simple, not uniform. It is fragmented, clumpy, with concentrations and gaps. And there are smaller streams, leading streams, trailing streams, branches, all torn from the Magellanic Clouds. The interaction between the Magellanic Clouds and the Milky Way is complex, dynamic, ongoing, and eventually, in a few billion years, the Magellanic Clouds will merge with the Milky Way. They will be consumed, their stars added to the halo, their gas added to the disk. This is galaxy evolution, in slow motion, visible, happening right now, in our cosmic backyard. There is a mystery about the lack of very massive stars. In the Milky Way, the most massive stars have masses around 100 to 200 times the mass of the Sun. But theory suggests that stars could form with even higher masses, up to several hundred solar masses. So where are they? Why do we not see stars more massive than about 200 solar masses? Perhaps they form, but they are unstable. They blow themselves apart before they can settle, before they can burn steadily. Or perhaps there is a physical limit, a maximum mass, beyond which stars cannot form, cannot accrete more material. The most massive stars have intense radiation, powerful stellar winds that push away the surrounding gas, that halt accretion. Perhaps that limit is around 200 solar masses. Perhaps that is the natural ceiling, the maximum, that physics allows. Or perhaps very massive stars do form, but they are rare, so rare that we have not found them yet, hidden in distant regions, obscured by dust. The most massive stars are also the shortest lived. They burn through their fuel in just a few million years, and then they explode, or collapse, and disappear. So even if they form, they do not last long. They are transient, fleeting. The mystery of the upper mass limit is one of the open questions in stellar astrophysics. We know stars exist up to about 200 solar masses, but we do not know if that is a hard limit, or just what we have observed so far. There is a structure in the Milky Way made entirely of old stars, the Hercules-Aquila cloud. It is not really a cloud, it is an overdensity, a concentration of stars in the inner halo, about 20,000 light-years from the galactic center, and it is enormous, stretching for tens of thousands of light-years, containing billions of stars. But these stars are old, ancient, metal-poor, part of the early galaxy, part of the first structures to form. The Hercules-Aquila cloud may be a remnant of an ancient merger, a dwarf galaxy that was consumed by the Milky Way long ago, and its stars now form this vast structure. Or it may be part of the original halo, a concentration that formed when the Milky Way was young, when the halo was still collapsing, still settling. We do not know. The structure is difficult to study. It is diffuse, spread over a large area, and individual stars are faint, distant. But it is there, a fossil, a relic, evidence of the early history of the galaxy, of how the Milky Way came to be. There is a mystery about the gap in the disk. Between the spiral arms, there are regions of lower density. This is expected. The spiral arms are where stars and gas concentrate. But there is one gap that is larger than expected, deeper, more pronounced. It is called the local arm gap, or sometimes the Great Rift, and it is near us. The Sun is close to this gap, close to the edge. The gap is not completely empty. There are stars, there is gas, but the density is lower, much lower than in the spiral arms. Why is this gap here? What created it? What maintains it? Perhaps it is a natural feature, the space between spiral arms, regions where density waves have not compressed the gas. Or perhaps it is the result of past events. Supernovae, stellar winds, that cleared out the gas, created a cavity, the local cavity, that we talked about earlier. Maybe part of this gap, part of this larger structure of low density. We live in a cleared region, a bubble, a gap, and that affects our view, our observations, the stars and nebulae we see nearby. There is a type of star that should not be in the Milky Way, high-velocity stars, not hypervelocity stars, but stars moving faster than normal, faster than the rotation of the disk. These stars have velocities that do not match the local standard of rest. They are moving through the disk, at odd angles, at high speeds. Some are moving toward the galactic center, some away, some perpendicular to the disk. And we do not know where they came from, why they are moving so fast, why their orbits are so strange. Perhaps they were born in a different part of the galaxy and migrated here through interactions, through orbital changes, or perhaps they are intruders from the halo, passing through the disk on elongated orbits, or perhaps they were accelerated by something, a supernova, a black hole, a close encounter with another star. Each high-velocity star is a mystery, a puzzle, and by studying them, we learn about dynamics, about orbits, about the forces that shape stellar motion. There is a mystery about the distribution of elements. When astronomers measure the abundances of elements in stars, they find patterns, trends, that tell us about nucleosynthesis, about where elements are made. Heavy elements, like iron, are made in supernovae, in the cores of exploding stars, and scattered through space. Other elements, like oxygen, are made in massive stars during their lifetimes and ejected in stellar winds and supernovae. Still others, like carbon, are made in dying low-mass stars, in planetary nebulae, released gently into the interstellar medium. But the patterns are not always what we expect. Some stars have unusual abundances, too much of one element, too little of another. These are called chemically peculiar stars, and they challenge our understanding of how elements are made, how they are distributed, how they are incorporated into new stars. Some of these stars may have formed from gas that was enriched by a single supernova, a single event. That dominated the local composition. Others may have accreted material from a companion star. That changed their surface composition, or they may reveal processes, physics, that we do not yet understand, new ways that elements are made, or moved, or transformed. Each chemically peculiar star is a clue, a piece of evidence about the complex history of matter in the galaxy. There's a place in the Milky Way where radiation is intense, the galactic center, again, not just because of the supermassive black hole, but because of everything around it. There are millions of stars, packed closely, many of them massive, hot, emitting intense ultraviolet radiation. There are supernovae, frequent, releasing high-energy gamma rays, X-rays. There are cosmic rays, particles accelerated to nearly the speed of light, by shocks, by magnetic fields, by unknown processes. And all of this creates a harsh environment, a bath of radiation, that permeates the region. If there are planets near the galactic center, they are bombarded constantly with radiation, with particles. Any atmosphere would be stripped away. Any life would struggle to survive, unless deep underground, shielded, protected. The galactic center is not a hospitable place, not for life, as we know it. But it is fascinating from a physics perspective, from an astrophysics perspective, because extreme conditions produce extreme phenomena, things we cannot study anywhere else in the galaxy. There's a mystery about the metallicity floor. When astronomers search for the most metal-poor stars, the oldest stars, stars with almost no heavy elements, they find a limit. No star has been found with absolutely zero heavy elements, completely pristine, completely untouched by previous stellar generations. The lowest metallicity observed is about 1/10,000th of the Sun's metallicity. Very low, but not zero. This suggests that even the oldest stars we can observe were formed from gas that had been slightly enriched by even earlier stars, by the truly first stars, population 3 stars, that we have never seen. Those first stars died, exploded, and enriched the gas just a little, and the next generation formed with that slight enrichment. And we see that next generation, but not the first. The metallicity floor tells us that we are always seeing second generation or later, that the very first stars are beyond our reach, forever hidden in the distant past. But we keep searching for stars with lower and lower metallicity, getting closer to that floor, trying to learn as much as we can about the earliest times. There is a structure in the Milky Way that might not be real, the Vela supercluster, or rather, the question is whether it is truly a structure or just a chance alignment. Near the constellation Vela, there is a concentration of old stars, an overdensity, a clump. Some astronomers think this is a real structure, a substructure in the halo, perhaps the remnant of an ancient dwarf galaxy. Others think it is just statistics, a random fluctuation, stars that happen to be near each other, in projection, but not truly associated. This is a common problem in astronomy. When we observe the sky, we see 2 dimensions, positions, angles. But the universe is 3-dimensional, and some things that look close together in the sky are actually far apart in space, and some things that look like structures, like clusters, like associations, are just chance alignments, determining what is real and what is projection. Requires measuring distances, measuring velocities, building a 3-dimensional picture. For faint, distant stars, this is difficult, uncertain, and so structures like the Vela supercluster remain ambiguous, possibly real, possibly not. The Milky Way is full of apparent structures, some real, some illusion, and disentangling them is part of the work of understanding the galaxy. You can feel the rhythm now, the slow, gentle rhythm of the galaxy, turning, orbiting, flowing, stars moving through space, through time, following paths set long ago by gravity, by history, by chance. And you are part of that, part of the flow, part of the motion, even as you rest, even as you lie still. The galaxy carries you, moves you, without effort, without thought, just the natural motion of everything together. And you can surrender to that, can let go, can drift with the current, with the tide, with the slow rotation of the Milky Way. There is a mystery about the tidal streams. We have mentioned them before, but their complexity, their variety, is remarkable. Some streams are narrow, pencil-thin, stretching for thousands of light-years, but only a few dozen light-years wide. Others are broad, diffuse, spread across large regions of the sky. Some streams are smooth, continuous, a steady flow of stars, following predictable orbits. Others are clumpy, fragmented, with gaps, with concentrations, as if something has disturbed them, perturbed them, and we do not always understand why each stream has the properties it does, why some are narrow, why some are clumpy. Part of the answer is the parent object, the globular cluster, or dwarf galaxy, that was torn apart. A compact object will produce a narrow stream. A diffuse object will produce a broad stream. But perturbations matter too. Encounters with dark matter clumps, with giant molecular clouds, with other structures, can create gaps, can create irregularities. By studying the detailed structure of streams, the clumps, the gaps, the wiggles, astronomers can learn about what has perturbed them, what has interacted with them, and this reveals the invisible structure of the galaxy, the dark matter subhalos, the distribution of mass, the gravitational landscape. Streams are like tracers, revealing the hidden architecture of the Milky Way. There is a place in the Milky Way where young stars are found in unexpected locations, above the disk, in the halo, where everything should be old, ancient, settled. But there are pockets, regions, with young stars recently formed, out of place. These are called high-velocity clouds that have formed stars, gas clouds, falling toward the disk, compressing, heating, and in some cases, collapsing, forming stars before they reach the disk, or perhaps gas ejected from the disk by supernovae that cools, condenses, and forms stars in the halo. Either way, these young stars are anomalies. They should not be there, should not have formed where they are, but they exist. And they tell us that star formation is not confined to the disk, that under the right conditions, stars can form almost anywhere, even in the halo, even far from the main reservoir of gas. There is a mystery about the oldest white dwarfs. White dwarfs are the remnants of sun-like stars after they die, after they shed their outer layers. What remains is the core, hot, dense, slowly cooling, and by measuring the temperature of a white dwarf, we can estimate its age. The cooler it is, the older it is. The coolest white dwarfs in the Milky Way are about 12 to 13 billion years old, almost as old as the galaxy itself. But here is the mystery. There should be even older white dwarfs, stars that died even earlier, in the first billion years of the galaxy's history. Where are they? Why have we not found them? Perhaps they are there, but too faint to detect. After more than 13 billion years, a white dwarf becomes extremely dim, almost invisible. Or perhaps the earliest stars were all massive, and they did not become white dwarfs. They exploded as supernovae, or collapsed into neutron stars or black holes. Only later, when lower mass stars formed, did white dwarfs begin to appear. This would explain the age distribution, the lack of extremely old white dwarfs. But we do not know for certain the population of the oldest white dwarfs remains uncertain. There is a type of cluster that is intermediate between open clusters and globular clusters. They are too old, too massive to be open clusters, but too young, too metal-rich to be globular clusters. These are sometimes called intermediate age clusters or young halo clusters, and they do not fit neatly into our categories, our classifications. Perhaps they formed during a transition period when the galaxy was changing from one phase to another, or perhaps they formed in special environments under unusual conditions that created something different. Each cluster is unique, has its own history, its own properties, and the existence of intermediate clusters reminds us that nature does not always fit into our boxes, our categories. That there is continuity, gradation, overlap between different types of objects. There is a mystery about the missing baryons. Baryons are ordinary matter, protons, neutrons, atoms, the stuff we are made of, the stuff we can see. But when astronomers add up all the baryons in the Milky Way, all the stars, all the gas, all the dust, they find that it is not enough. Based on cosmology, based on the Big Bang, we know how many baryons should exist in the universe, what fraction of the total mass. But when we look at the Milky Way, we cannot account for all of them. About half are missing. Where are they? Where did they go? One possibility is that they are in the halo, in a hot, diffuse, ionized phase, too hot to emit much light, too diffuse to detect easily. This is called the circumgalactic medium, the gas surrounding the galaxy, extending far beyond the disk. It may contain as much mass as the disk itself, but spread over a much larger volume. Another possibility is that the baryons are in structures we have not yet mapped, dense clouds hidden by dust or in regions we have not surveyed, or perhaps some baryons were ejected, blown out by supernovae, by galactic winds, and now reside in the intergalactic medium beyond the galaxy, lost. The missing baryons are one of the puzzles of galactic astronomy. We know they should be somewhere, but we cannot find them all. There is a place in the Milky Way where the magnetic field reverses. Magnetic fields have direction. They point from north to south, from one pole to another, and in most of the galactic disk, the field points in one direction along the spiral arms, following the rotation. But there are regions where the field flips, reverses, points the opposite way. These are called magnetic reversals or field reversals, and we do not fully understand how they form, what causes them, what maintains them. Perhaps they are relics of past events, disturbances that twisted the field, created irregularities, or perhaps they are part of the dynamo, the process that generates the magnetic field. Reversals may occur naturally as part of the cycle on Earth. The magnetic field has reversed many times throughout history. North becomes south, south becomes north. Perhaps something similar happens in the galaxy, but on much larger scales, much longer time scales. Magnetic reversals are another reminder that the galaxy is not static, not simple, but dynamic, complex, full of structures and processes we are only beginning to understand. There is a mystery about stellar ages. Measuring the age of a star is difficult, uncertain. We can measure brightness, temperature, color, composition. But age is more challenging. One method is to use stellar models, simulations that predict how stars evolve over time. By comparing observations to models, we can estimate how long the star has been burning. But this depends on the models being correct, and there are uncertainties in the physics, in the nuclear reactions, in the mixing of material. Another method is to look at stellar clusters where all stars formed at the same time. By studying the cluster as a whole, we can estimate its age, and then individual stars in the cluster have the same age, but isolated stars, stars not in clusters, are more difficult, and sometimes we find contradictions. A star that looks young but has old composition, or a star that looks old but is in a young region. These anomalies reveal that stellar evolution is more complex than our models suggest, that stars can rejuvenate, can merge, can change in unexpected ways. Age dating remains one of the challenges in stellar astrophysics. There is a structure in the Milky Way That is invisible in most wavelengths. The North Polar Spur. It is an enormous arc of radio emission stretching across the sky from the galactic plane toward the North Pole, and it is very large, spanning more than 100 degrees, more than half the sky. For decades, astronomers thought it was distant, thousands of light years away, part of a supernova remnant in the disk. But recent measurements suggest it may be much closer, only a few hundred light years away. If this is true, then the North Polar Spur is part of the local bubble, the cavity we live in. It may be the edge of the bubble, the shell where the expanding gas from past supernovae is interacting with the surrounding medium. But the nature of the spur is still debated, still uncertain. Different studies give different distances, different interpretations. It is one more mystery. In our immediate neighborhood, a structure so close that it spans half the sky, and yet we do not fully understand what it is. There is a mystery about runaway stars. Some massive stars are moving very fast through the galaxy, not as fast as hypervelocity stars, but faster than normal. These are called runaway stars or walkaway stars, depending on their speed, and we think they were ejected from binary systems. If a massive star has a companion and the companion explodes as a supernova, the explosion can kick the surviving star, accelerate it, send it speeding away. Or if two stars are in a crowded cluster, gravitational interactions can eject one of them, launch it out of the cluster. Either way, the star ends up moving fast through space away from its birthplace. Runaway stars are interesting because they carry the imprint of their origin, of the event that accelerated them. By studying their velocities, their trajectories, we can trace them back to their birth clusters, to the regions they came from, and sometimes we find that a runaway star and a supernova remnant are connected, that they both came from the same binary system. This helps us understand stellar evolution, binary interactions, how stars live and die together. There is a place in the Milky Way where something is orbiting that we cannot explain. Around the supermassive black hole, at the galactic center, there are objects called G objects. They look like gas clouds, extended, diffuse, when they are far from the black hole. But when they pass close to the black hole, they do not behave like gas clouds. They do not get stretched, do not get torn apart by tidal forces. Instead, they remain compact, intact, as if they were solid objects, but they look like gas, not like stars, not like solid bodies. What are they? what could be, compact enough to resist tidal forces, but diffuse enough to appear like gas. One idea is that they are stars surrounded by thick envelopes of gas and dust. The envelope makes them look diffuse, but the star at the core provides the mass, the compactness. Another idea is that they are binary stars in the process of merging, surrounded by material ejected during the merger. Or perhaps they are planets stripped from their stars by the black hole and surrounded by atmospheres that have puffed up in the heat. We do not know. G objects are strange, unusual, and we are still trying to understand what they are. There is a mystery about the scale height of the disk. The scale height is the thickness of the disk, the distance above and below, the plane where most stars are found. And the scale height varies for different populations of stars. Young stars have a small scale height. They are concentrated near the plane. Old stars have a larger scale height. They are more spread out, more vertically extended. This makes sense. Young stars are still near their birthplaces in the disk. They have not had time to be disturbed, scattered. Old stars have been around longer. They have been perturbed by encounters with giant molecular clouds, by spiral arms, by the bar, and over time, these perturbations heat the disk, puff it up, increase the scale height. But the rate of heating is uncertain. The mechanisms are complex, and the observations do not always match the models. Some populations have scale heights that are too large or too small for their age, and this tells us that disk heating is not a simple process, that there are additional factors, additional mechanisms we have not fully accounted for. You can feel your body now settling, sinking into the surface beneath you, supported, held. There is no need to hold yourself up, no need to maintain tension or alertness. Just let go. Let your muscles soften. Let your breathing slow. Let your thoughts drift like stars through the halo, moving without direction, without purpose. The Milky Way holds billions of mysteries, and you do not need to solve them, do not need to remember them. Just let them pass through your awareness like light through space, gently, quietly, without resistance. There is a mystery about the gamma-ray glow. When astronomers observe the Milky Way with gamma-ray telescopes, they see a diffuse glow coming from the galactic center, from the bulge, from the disk. Part of this glow is expected. Cosmic rays colliding with gas, producing gamma rays through known processes. But there is excess emission, more gamma rays than expected. more than can be explained by ordinary processes. This excess is called the galactic center, GeV excess, and it has puzzled scientists for years. What is creating these extra gamma rays? What is producing this unexpected glow? One possibility is dark matter. If dark matter particles can annihilate when they meet, they could produce gamma rays, and the signal would be strongest where dark matter is most dense, at the galactic center. This would be revolutionary, direct evidence of dark matter revealing itself through radiation. But there are other explanations, more mundane. Perhaps there are more pulsars than we have detected, each emitting gamma rays, and together they create the excess. Or perhaps there are more cosmic ray sources, more supernovae, more acceleration sites, creating more gamma rays than we accounted for. The debate continues, the observations continue, and the mystery remains unresolved. It may be dark matter, or it may be something we have not considered, something unexpected, something new. There's a place in the Milky Way where stars have strange chemistry, the Omega Centauri globular cluster. It is the largest, brightest globular cluster, visible from the southern hemisphere, containing about 10 million stars. But Omega Centauri is unusual. Unlike other globular clusters, its stars do not all have the same composition. There are multiple populations with different metallicities, different abundances, as if they formed at different times from different gas. This suggests that Omega Centauri is not just a globular cluster. It may be the core of a dwarf galaxy that was consumed by the Milky Way. The outer parts were stripped away, scattered into streams, but the core remained intact. And what we see now as Omega Centauri is the remnant, the survivor. If this is true, then Omega Centauri holds secrets about galactic collisions, about how galaxies merge, about what happens to the cores of smaller galaxies when they are captured. It is a time capsule, a relic of a galaxy that no longer exists except as this massive cluster orbiting the Milky Way. There's a mystery about the asymmetry. The Milky Way is not perfectly symmetric, not perfectly balanced. When we map the distribution of stars, the distribution of gas, we find asymmetries, lopsidedness, one side slightly different from the other. The northern half of the disk is not identical to the southern half. There are differences in density, in star formation, in structure, and the disk is not centered. On the galactic center, it is offset, slightly shifted. These asymmetries are subtle but real, and they tell us that the galaxy is not in equilibrium, not perfectly settled. Perhaps it is still responding to past events, to collisions, to mergers that happened millions or billions of years ago. Or perhaps it is being perturbed right now by the Magellanic Clouds, by other satellites, by the flow of gas. Galaxies are not static structures. They are dynamic, constantly adjusting, constantly responding to forces, both internal and external. The asymmetries in the Milky Way are evidence of that ongoing evolution. There is a type of star that contains technetium. Technetium is an element that does not exist naturally on Earth. It is radioactive. It decays too quickly to have survived since the formation of the solar system. But in some stars, technetium has been detected in their atmospheres, in their spectra. How is this possible? How can a star contain an element that decays so quickly? The answer is, the star is making it right now. These stars are called S-process stars, or technetium stars. They are red giants, undergoing nuclear reactions in their interiors through a process called the S-process, the slow neutron capture process. They are creating heavy elements, including technetium, and convection brings these elements to the surface where we can detect them. The presence of technetium tells us that nucleosynthesis is happening right now inside the star, that elements are being forged as we observe. It is direct evidence of stellar alchemy, of the processes that create the elements in the universe. There is a mystery about the thick disk stars near the Sun. We mentioned the thick disk earlier, a population of old stars, above and below the thin disk. But near the Sun, we find thick disk stars that are moving in unusual ways. Their orbits are strange, eccentric, tilted, and their ages do not always match their chemistry. Some have old compositions, but appear relatively young. Others have young compositions, but appear old. These discrepancies suggest that the thick disk is not a single population, not a simple structure. It may be a mixture of stars from different origins, some formed in place, others accreted from satellites. Each star has its own history, its own journey, and by studying these individual histories, we can piece together the larger story of how the Milky Way assembled itself. There is a place in the Milky Way where nothing seems to form, a star formation desert. In some regions of the disk, the conditions seem right for star formation. There is gas, there is dust, there is density, but no stars are forming. The region remains quiescent, inactive. We do not know why, what is preventing the gas from collapsing, what is supporting it against gravity, perhaps turbulence. The random motions of the gas provide pressure that counteracts gravity, or perhaps magnetic fields thread through the gas and provide support, preventing collapse. Or perhaps the gas is simply not dense enough, not quite at the threshold for collapse. These star formation deserts remind us that star formation is not automatic, not inevitable, that there are barriers, thresholds, conditions that must be met, and that even when conditions seem right, other factors may intervene, may delay or prevent the formation of stars. There is a mystery about the warps in stellar streams. Some tidal streams show kinks, bends, changes in direction that do not match simple models of tidal disruption. These warps may be caused by encounters with dark matter clumps, massive concentrations of dark matter that pulled on the stream as it passed by. If this is true, then by studying the warps, measuring their size, their location, we can map the dark matter substructure in the halo. This is one of the most promising methods for detecting dark matter clumps indirectly through their gravitational effects on visible matter. But the interpretation is complex. Other things can create warps, giant molecular clouds, satellite galaxies, the bar, the spiral arms. Distinguishing between these different causes requires careful analysis, detailed models, precise measurements, but the potential is enormous. Streams may be our best window into the detailed structure of dark matter. In the Milky Way, there is a mystery about how the galaxy will end. What is the ultimate fate of the Milky Way? We know that in about 4 billion years, the Milky Way will collide. With Andromeda, the two galaxies will merge. The result will be a large elliptical galaxy, Milkomeda or Milkdromeda. But what then? What happens after the merger? The combined galaxy will contain hundreds of billions of stars. It will be one of the largest galaxies in the local group, and it will continue to evolve. Stars will form from the remaining gas for a time, but eventually the gas will be exhausted or heated or expelled, and star formation will cease. The galaxy will age, the stars will burn out, one by one. The brightest will die first, then the middle-sized eventually. Only red dwarfs will remain, and the galaxy will fade, redden, darken. Over trillions of years, most stars will be ejected through gravitational interactions, flung out into intergalactic space. What remains will spiral inward toward the center, toward the merged, supermassive black holes, and eventually the galaxy will be gone, dispersed, dissolved. Only black holes and dead stars scattered through the void. This is the long-term fate of all galaxies in a universe dominated by dark energy, expansion, isolation, aging, dispersal, a quiet end, a slow fade, not a collapse, not an explosion, just silence. But that is trillions of years away, far beyond any timescale we can truly comprehend. For now, the Milky Way is alive, active, evolving, and we are here to witness it, to study it, to be part of it. There is a wonder in simply existing within the Milky Way, in being one small part of this vast spiral structure this collection of hundreds of billions of stars, each star a sun, perhaps with planets, perhaps with moons, perhaps with life, all of it, bound together by gravity, moving together through space, orbiting the common center. We are galaxy citizens, residents of the Milky Way, participants in its story. And that story is still being written, still unfolding. The Milky Way is not finished, not complete. It is merging with smaller galaxies, growing, changing, evolving. It is forming new stars, creating new planetary systems, new possibilities. It is a living structure, dynamic, complex, beautiful, and every mystery we have explored tonight, every puzzle, every question, is part of that beauty. The unknown is not a problem. It is a gift, an invitation to wonder, to explore, to discover. The Milky Way does not reveal all its secrets at once. It shares them slowly, gently, over time. And we are patient. We watch, we measure, we learn, and gradually the picture becomes clearer, the story becomes richer, the mysteries transform into knowledge. But new mysteries always emerge. Each answer leads to new questions. The exploration never ends. And that is as it should be, because the universe is infinite in its complexity, in its depth, in its capacity to surprise us. You can rest now in the knowing that you are part of this, part of the Milky Way, part of the cosmic story. Your body is made of elements, forged in stars, scattered by supernovae, gathered by gravity, assembled into life. You are stardust, given form, given consciousness, given the ability to wonder about the galaxy that made you. And tonight, as you rest, as you drift toward sleep, the galaxy continues turning, the stars continue shining, the gas continues flowing, the mysteries continue waiting, all of it happening slowly, quietly, patiently. And you can let go now, can release the need to know, to understand, to stay awake. The Milky Way will be here tomorrow and for billions of years to come, and you are part of it, always connected, woven into the fabric of the galaxy. Rest now in that connection, in that belonging, in that peace. Let your breathing slow, let your thoughts fade, let sleep come gently, naturally, inevitably. The mysteries will wait, the wonders will remain, the Milky Way will continue its slow, eternal dance, and you can sleep now, deeply, peacefully, held by the galaxy that is your home. Sleep rest be, here, in the spiral arms of the Milky Way, in the quiet, darkness, between the stars, in the ancient, patient peace of the galaxy. Sleep now, sleep.